All right. It is 8:30. Good morning, everybody. If you're online, can you hear me? If someone can give me a thumbs up.
Yes.
Okay, great. So this is the winter Land Working Group meeting. And we're gonna have a series of talks this morning. I'm Gunther Legge, the co-chair of the Land Working Group. Mary Ruscano is also here, so the co-chair of the Land Working Group. We have Kate, who's with us too, the software liaison, and Bill Lipscomb, the main citizen developer. So if you have any specific citizen question, we hopefully will be able to answer all of them. Before we start, I just want to remind everybody that this is a very friendly meeting. It's not that many of us, so it's serious but laid back. Just want to remind everybody to be respectful with each other, be collaborative, consider different opinion. It's okay to disagree. Communicate openly, be mindful of others, and in particular for those of you who's maybe the first time joining us or you don't join us very often, I just want to remind you, don't be shy. There's no stupid question. Even within the cryosphere science, we have specialties in many different areas that we might not know about a lot about. So it is definitely okay to ask a question that might make you uncomfortable, but it might make you uncomfortable for 2 seconds, and then you'll be happy to be able to follow the rest of the conversation that is going on. So, yeah. Before we start here, I just want to thank all the administration team that made this meeting possible, from the administrative team to the IT team, and they are monitoring us very closely. You saw Kenan and Teresa Waltz outside, but you've been in touch with Elizabeth Fairclough, who sent out some announcement and reminders. Okay. This meeting is going to run until noon today. We have a total of 9 talks in discussion time, and at the end of the morning, we're going to adjourn and have lunch at the cafeteria here at the Mesa Lab. We have a table reserved for us to continue our discussion, either about science or else, or just checking in on each other. The first session of the morning is going to be led by Kate, and she's going to remind everybody that you have 13 to 15 minutes for your presentation and leave 3 to 5 minutes for questions. And if you hear her saying 2 minutes or your time is up, well, you know what it means. And Miriam will do the same for the second part of the session. So please mute your cell phone if you haven't already. If you're online, please join us using companion mode if you can, more particularly in this room, so it doesn't echo with the audio devices. So I will turning to you, Kate, and let me bring up the first talk of the morning.
Yeah, our first talk this morning is Richard Slither. Okay. From NASA. I'll start the timer once they get things going, but
Let's see.
when did she sit? We're good to
Can I present from my chair?
Sure.
Yeah. Okay.
Oh, that's
You don't
right,
need
because
a
Gunter's
microphone.
going to do the slides for you.
Okay.
Hey Gunter, it's already on the desktop.
On Google Drive.
I think you have to download it.
Oh, no, it's right on the desktop.
There you go.
So I'd like to thank Gunter and everyone for allowing me to present this morning. So my co-authors are part of a NASA project looking at the surface representation of the Greenland ice sheet. We also have other co-authors who are involved with projects at the GMAO. Next slide, please. So the GMAO is the Global Modeling and Simulation Office at NASA Goddard Space Flight Center. So we have several major efforts associated with global Earth system modeling. They're weather analysis and prediction, seasonal prediction, reanalysis, global mesoscale modeling, and observing system science. So most of our efforts revolve around our GEOS Earth system model. It can be coupled with various ocean models. For our subseasonal seasonal prediction system, we couple with the GFDL MOM model. But we have several configurations. We have a very high resolution convective preventing model. We produce observing system simulation experiments. We have several chemistry configurations for the GEOS model. And something I'll be talking about a little bit more is the GEOS land surface model, which has also recently been as incorporated land ice representation as well. So we have several products that are relevant to the polar regions. We have a routine numerical weather prediction forecasting system, GEOS FP, that gets updated quite regularly. We have a reanalysis that is internally given to satellite system representatives for configuring their sensors and things like that. That's known as GEOS IT if they need meteorological information. We have a composition forecast system, which has recently been updated. That's GeoCF2. And we have our seasonal prediction system. And we have reanalyses. Next slide, please. So the polar regions and the polar ice sheets have particular focus for the geosystems. They are known to be challenged for some of our products. Reanalyses have particular issues. Numerical weather prediction has particular issues for high latitudes. But we also have an enhanced focus for particular things that NASA is interested in: sea level prediction and understanding of sea level. And the significant role of the polar regions in recent changes in conditions. Next slide. So I thought I would say a little bit about our coupled ice sheet model efforts. We have been working on coupling with the JPL ISSM model. So our previous effort, which spans quite a long period of time now, utilized an aspect of the GEOS model. The GEOS model works on an exchange grid, so it has various land surface tiles. Each of those tiles produces a energy flux, which is then amalgamated to communicate with the atmospheric grid boxes. So we have this high resolution subgrid scale land surface model running. So we initially wanted to have a given tile be assigned to each ISSM element. So that's very practical if you're, around 70,000 ISSM elements. However, more recent simulations, simulations of the Greenland ice sheet involve, 100,000 to 1 million or more elements for the ice sheet. So this is no longer practical. So recent efforts are led by Aaron Stubblefield and Lauren Andrews. They have been looking at more of a disconnect between individual tiles and the land surface elements. So an interpolation or some other type of means of communicating between the land surface tiles and the atmosphere. So the ISSM elements. So that's part of the thing. Aaron has been working on a coupler, which has gotten around some of our historic ESMF issues with with coupling with the system, and so that has progressed. Lauren has outlined here in this diagram a future configuration which would involve the community fern model as well as the snow model that I'll talk about here later, and various ice sheet models. So that's essentially where we are at the moment. Next slide, please. So this is a look at some of the GMAO reanalysis products and the history of them. So we originally produced MERA reanalysis, I guess around 2009, 2010 or so. MERA 2 was produced around 2016, I'm going to say, and it had several associated model systems associated with that. The Merit 2 Scream, stratospheric chemistry, and other things as well. So in the latest iteration of our reanalysis products, we have GEOS IT, which is this internally distributed instrument team reanalysis, which is distributed. That's a 3D VAR system. And we have in production Merit 21C. So Merit 21C is our first hybrid 4D ensemble variational reanalysis system that will be completed later this year, and there'll be a distribution system after that. There are several systems or products that will be associated with these products. One of them will be Merit 21C Polar, which will be a 7-kilometer downscaling system. So Merit 21C is a kind of interim reanalysis for the 21st century. We have thoughts and planning for newer reanalyses that will cover longer periods of time. Next slide, please. So it's hard to say everything that has changed for our system since 2016. I think it would be easier to give a list of what has not changed. I think for the Greenland ice sheet and things like that, some of the main changes have been we've gone from Chow-Suarez radiation scheme to RRTM radiation. So historically, we've had a very good climate for the Greenland surface. With RRTM, we now have an additional 30 watts coming down at the surface that we need to accommodate for that, and that is what we're going to work on. But Merit 21C again has this 4D ensemble variation. It has newer analyses and newer constraints for sea surface temperature and other things as well. Okay, next slide, please. Okay, so this is a look then at surface mass balance for some of the products that we produce. So on the far left is our historic Merit 2 reanalysis. GI Ocean is essentially the initial condition for our new coupled system seasonal forecasting. That is a weekly coupled atmosphere ocean assimilation system that replays to this GEOS IT reanalysis, and it incorporates a 2-moment cloud microphysics. GEOS LDAS is an offline land system model, so essentially the land component of the GEOS system that is forced with an atmospheric reanalysis. Then I have selected years for Merit 21C that have been completed from the 3 streams that are running. And on the far right, I had what I could find, which was the RECMO 2 climatology. So each of these generally show, basic essential features of the Greenland ice sheet. They have various differences that are associated with the atmospheric forcing. Next slide, please. So this is a time series of annual values for the surface mass balance, precipitation, and runoff. So you can see that there is, despite various similarities in our systems, there are quite big discrepancies between the two. Merit 2 is known to have a lot of precipitation over the Greenland ice sheet, and the Arctic in general, and that has been reduced in newer reanalysis systems. I would say here, though, that based on changes in our annual atmospheric forcing, the precipitation has about a 11% range from the median for precipitation, whereas runoff is kind of a summation of changes and feedbacks associated with surface precipitation, the albedo feedbacks, and other associated feedbacks, and so the changes are on the differences are on the order of 40% for the various systems. Okay, next slide, please. So a lot has changed in the GEOS system. One thing that has not changed that we would like to further address is the surface representation and the surface hydrology. So we have a surface representation of intermediate complexity. It's based on the Stieglitz model. It's based on prognostic variables of layer thickness, the water equivalent amount, and a mass, and the heat content. So it does not have an explicit representation of Föhn. It does have fractional snow cover, snowpack cover. So you can have bare ice conditions. That was one of the things that we were interested in. It has meltwater percolation and refreezing within the snowpack. Okay, so we would like to take a look at this, and based on our new atmospheric forcing, but also based on new observations, try to revamp what we have. Okay, next slide, please. Okay, so one of the things that we're using to revamp is a product produced by Andreas Kolander and Amalgar Hassan at JPL, and they have produced a quantitative estimate of meltwater for the ice sheet. So historically, one would look at the melt area. That's a readily produced variable from passive microwave that shows the areas for the melt over the Greenland ice sheet. This retrieval from JPL is a volumetric retrieval based on the sensitivity relative to climatological values for radiances based on various levels. So right now we have a column integrated that is based on SMAP and AMSR2. So we would like to evaluate, we would like to use that for our evaluation. Okay, next slide. So these are some comparisons. This is with available years from MERIT 21C. So the main result initially that we find is that MERIT 21C and most of our system, or all of our systems, essentially have much less meltwater content within the snowpack than is shown by the satellite retrievals. So it's, you know, for the pan ice sheet, it's on the order of, you know, 50% or more, but in many areas it's much less. So that is one of the things we'd like to understand a little bit better, is the amount of meltwater contents. Next slide. So this is our offline GEOS LDAS that we have been using for as kind of a basis for our understanding of our system. It shows similar differences. On the right, I've also shown some estimates for the snowpack cover. So in addition to, you know, the production of meltwater, for validating meltwater content, you'd also need a snowpack in order to have meltwater. And I've showed some variables here for the snowpack and the snow depth over the ice sheet. So we've been using those as constraints on comparing with the SMAP-derived values. But certainly that is also an issue that we'd like to look at further, is, you know, how can we validate our snow cover as well? Okay, next slide. So one of the variables that we've been looking at for trying to understand these differences is the holding capacity of meltwater within the snowpack. So historically, we used the Stieglitz model as it was configured for terrestrial land cover. And when it was initially configured, they wanted a lot of runoff. So they had very small amounts. 1% was the baseline for previous systems for the meltwater holding capacity. So we've done some experiments here for increasing the holding capacity to 2%, 5.5%. And you can see that for most regions at 5.5%, which I think is a reasonable value, that was the value originally quoted by Stieglitz. You see there's pretty good agreement, particularly for the southwestern Greenland. Now for southeastern Greenland, you can see at 5.5%, there's quite a bit of over a value greater than has been observed by SMAP. So there's also questions about SMAP, of course, because SMAP is radiance looking down, and so it's trying not to sense the supraglacial aquifer that is in southeastern Greenland. But that's another issue. Next slide. So these are some differences in the holding capacity, or these are differences in the meltwater content on the far left. But you can see, so that has gone up when you change the holding capacity, but of course the runoff has now gone down considerably. And so you have these differences in the surface mass balance that are particularly noted in southeastern Greenland. You have more surface mass balance because you've essentially eliminated the runoff. I think my last slide is next. Yes, so I've shown some new products. So we are evaluating using GEOS LDAS our novel observational estimates of meltwater content, and we're going to use those to configure the land surface hydrology for new systems. We'll also be using the LDAS for data assimilation as well. And that's my talk.
Nice. I have a question, but I'm going to let other people go first. Are there any questions in the room? Yeah.
Great diagnostics. Are you going to share them with other folks, like people like us?
So the SMAP
Yeah.
data, yes, I believe JPL has plans for releasing them. I think they might have released some of it so far. Some of their work is under review still. So, but of course we will share that with the rest of the community.
Yeah, great.
I think they have a paper published, and so you should be able to find the data associated with that paper, but they're still like continually updating their product. So yeah, I guess theoretically they'll release evolved versions of it at some point.
Very cool.
I have a silly question. Can you go back a slide? Is Ellesmere Island included in your domain here? I just kind of wonder what's going on with the Canadian Arctic there.
Yeah,
Seems to be some really big differences.
well, so here I show surface mass balances computed over all land surfaces, so including land ice. You can see that for, oh, this is for the LDAS. So the LDAS is only showing values for the glaciated land, so land ice category. So I think the far eastern part of Ellesmere is glaciated, and that's what you're seeing. Northern Canada has historically been an issue in our reanalyses. It's been too cold and perhaps too dry. And I think the newer systems are showing better values for those areas.
If you're referring to the sharp line, I think it's because I set a longitude domain on the run.
Okay.
So it's just not computing values more than to the
Okay.
left.
Yeah.
It's Filipino.
Yeah.
I think, so this is just looking at the LDAS system. So I think this is the glaciated land part, right?
No, it's because to speed up the runs, I set longitude domains on where tiles that it was
gotcha.
going over, and so it's
Gotcha.
just not doing it over those tiles.
Okay. But in the leftmost, there's a lot more of Ellesmere included.
Right, so that was like a global run.
Okay.
Yeah.
Oh, interesting. So I don't know a lot about GEOS, and you were talking about coupling the atmosphere one file per element. I was curious, do you couple to the ocean for runoff in a similar way, or?
So right now, the coupling efforts are just falling associated with the atmospheric model, GEOS atmospheric model. So I've thought about coupling with the ocean,
Yeah.
but that's in the future.
Right. Sounds good. Are there any questions online? All right, thank you so much. All right, our next talk is Gigi Yin. So are you, yeah, go ahead and speak if you can.
Hey, Gunter, the presentations are
Can
already
you share-
downloaded on
Do we
the.
need to stop sharing from yours?
No, they're
Would you like
they're
to present from
downloaded
your
on
computer?
Yeah.
on the
yeah.
desktop.
Yeah.
Too. Sorry.
Try.
Hey, that works good.
Oh, yeah. Okay. Yeah. So I'm Ziggy from CU Boulder. I'm a 5th year PhD student, and today I'm going to present my last PhD project, and these are my collaborators on this work. So the surface melt of Greenland ice sheet is driven by this interaction between the atmosphere and the ice sheet surface with both local and remote processes. And simulating large example of surface melt fields using climate models is computationally expensive. So, and also most Simi6 models, they lack realistic surface melt calculation over ice sheets. So so machine learning emulator to emulate surface melt views become a alternative way, like trained, for example, trained with CSM2 data, and which is a alternative way to produce such large ensemble, and it's easier to like do sensitivity experiments with with this emulator. And our work is built on previous work published by Selward et al. 2021. They develop a one-dimensional neural network emulator to predict the integrated melt, surface melt of a Greenland ice sheet. And in our work, we are trying to develop a 2D emulator to predict the spatial surface melt views. And we built our emulator based on graph neural network. Graph neural network has been successfully applied in some of the machine learning-based weather prediction models, like the GraphCat. And because our goal is to emulate annual surface melt view, so on annual timescales, the surface melt can both be like caused by local drivers and also remote processes like large-scale circulation. So we also add another layer of global attention to make this combined method called a graph transformer. So the global attention layer is built on a self-attention mechanism and allow the emulator to dynamically weigh the input of its different elements. So in this way, we can integrate both like the message passing from neighboring nodes and also the message from remote nodes. And such combined method has been applied to, for example, the AI forecast system of the ECMWF. The data we are using for training and validation are the CSM2 large ensemble, which has 100 members for both the historical and the SSB3 scenarios. And we use the first 19 members for training and the last 10 members for validation. And the testing data are the CMIP6 ensemble, which has 11 historical members and 3 members for each SSP scenario. And this strategy allow us to also to evaluate the generative ability of this model, this emulator, because during the training we don't have SSP5 scenario, and we want to test it on these unseen like samples to see if the emulator can predict like the distribution that is out of the sample. The input variable we have is 12 variables from CSM2. They are the downward shortwave radiation, long-wave radiation, 2-meter temperature, surface temperature, 2-meter specific humidity, and wind speed, surface pressure, fail 100 geopotential height, and the snow, rain, cloud water pass, and also integrated water vapor. So these input variables are input as a JJA mean field for each year, and our output variable is annual surface melt views over the Greenland ice sheet. And so the input variables are from this latitude longitude grid box shown in the right, which covers like the Greenland region and also Greenland blocking region, and also most of the North Atlantic, which can have impact on the Greenland ice sheet. And this shows the structure of our emulator. So in addition to these input variables, we also have latitude, longitude as a positional encoding into the emulator. And we use a statistical method of GNN called GTGCN, and a method called Performer, which is the the global attention layer, which use linear attention, so it's more scalable to large scale data compared to transformer model. And our loss function is a mean square area over the Greenland ice sheet. And in addition to area weight, we also add an elevation weight that has a larger weight over the lower elevation to stress more of the large melt area. And I first trained this emulator on my laptop, and it takes about 5 to 30 minutes for different settings for each epoch. And then I moved to a GPU on the Texas Advanced Computing Center, and it's about 30 times faster than on my laptop. And we applied the early stopping criteria. So for the training, so if the validation loss didn't improve for 10 consecutive epochs, we save the model parameter corresponding to the minimum loss. And basically, we can see this template, like they stop after about 70 to 100 epochs. And first, I'd like to also we evaluate the emulator based on like for considering all the ice-sheet grid cells, and we use the matrix mean RMSE, basis, and R square. So this we compare our emulator with 2 baseline methods, which is per grid cell linear regression and also per grid cell random forecast. And for the emulator, we use 2 different settings. So one is a pure graph neural network without the global attention, and another setting is with combined graph neural network with global attention, and we tested 2 layers and 4 layers. So if we compare these 2 baseline methods, like we can see the random forecast has better performance than linear regression, and that indicates on an annual time scale, the surface melt has the melt mechanism has not only linear relationship, but also has a non-linearity in the melt mechanism. And we can also see, if we compare the GNN with these baseline models, we can see the GNN outperforms the baselines, and that indicates, so at this time scale, the melt is not only like impacted by the local node, also by its neighboring nodes. And when we add global attention, we can see this further improve this performance of the emulator. So that indicate it also have impact from remote node, which is captured by this global graph transformer emulator. And there isn't too much differences between 2-layer and 4-layer graph transformer. So in the later evaluation, we use this 2-layer graph transformer setting. And this is just an example of the emulated melt field for 1 year, is 2014. So on the left panel, left 2 panel shows the CSM2 simulated surface melt, and the second panel shows the predicted melt by the emulator. So we can see the emulator is the general spatial structure of surface melt. And if we look at the third panel, which is the difference between these 2, we can see the emulator has some like overestimation over some of the basins and underestimation over the other basins, so like especially over the lower elevation regions around the ice-sheet margins. I think that is because it's challenging for the emulator to predict where the like the surface melt has a sharp gradients. And if we divided this difference field by the CSM2 simulated melt in the fourth panel, so we can see over this ice-sheet margins, like large melt regions, the percentage of this pass is around, I think it's around maybe 10% or below. And then this is a similar evaluation, but instead of a single year, but average over the historical period or the future scenario. And we can look at this right figure first. So this show the three lines shows the historical period and SSB3 and SSB5. So if we look at the left two column, which is the RMSE and this percentage, so we can see it's also similar to what we see before. So it has basically it has large RMSE over the marginal regions, which can be up to like 300 millimeter per year, but over the interior is much smaller. And again, this the percentage of the basis is around maybe 5% for historical and SSB3, and we did see a large basis in SSB5 because of the out of sample distribution of the melt values. And the right two columns shows the basis and the percentage of the basis. And basis has a much smaller magnitude compared to RMSE because the positive and negative basis, they cancel out each other. So we have this relatively small value. In the left, it just shows the scatter plot of all the grid cells for all these different years. And we have a good agreement between this predicted melt and simulated melt. The blue color shows the points from the SFC5 scenario, and we can see it has some underestimation over very large melt values, which is more easier to see in this integrated melt time series. So in this plot, the black lines shows the simulated and emulated historical melt, and the color line shows different SSB scenarios. The solid line represents the CSM to simulated melt, and dashed line is the emulated melt. So we can see this for historical and SSB 1 to 3 scenarios, the emulator has very similar like integrated melt compared to the CSM to simulated values. But we did see for SSB5, so it is purple lines, especially over the last 20 years, we have this significant underestimation of the integrated melt field. And this happens over the last 20 years of the century because this last 20 years exactly where the simulated melt values are above all the training distribution, like compared from historical to SFB3. And we did see the emulator has some generative ability to predict this larger melt than the training distribution, but it's still the ability is limited. So yeah, I think also this is challenging for a machine learning emulator to predict out of the sample. So the major takeaway so far is that the emulator can produce reasonable CSM2 annual surface melt fields and can capture the interannual variability well. But it has relatively large basis over the large melt regions over the green acid margins. And also the emulator shows some but limited generative ability to predict out of the sample, like in the SSB5 scenario. And next steps for this is I will try to see if I can further improve the emulator to predict for the SSB5 scenario. And also at the same time, I have started to use feature attribution to identify the key atmospheric variables and regions that controlling surface melt of a specific region over the ice sheet, whole ice sheet. And after that, I will apply this train emulator across different the Sim6 models to get the ensemble spread of the melt prediction. Yeah, thank you very much.
Great, thank you. Are there any questions in the room?
Sure, I can ask one.
Go.
How did you select which variables are going into your emulator? Did you do any experiments on that?
Yes. So, I first has the 5 input variables that used in this previous study that they built a 1D emulator. So I think it's in downward shortwave, long wave radiation, 2-meter temperature, snow, and also drop dash height, I think. And also attached to this, and the other variables added is based on like literature, like which variable might impact surface melt. And we did several experiments like adding additional variables like surface melt, surface temperature, which is we see that further improve the performance of the model. So that's how we decided the current variables. But we think we haven't tested like all variables, so there might be some redundant variables in the current size.
Okay.
I have one question. Great talk. One question that's in your future plan.
Yeah.
You mentioned that over some places you may need remote information in order to better reproduce the variable you are looking at. You mentioned that you may use feature selection or attribution trying to identify that. I'm wondering whether there's any method you can validate the process you identified. How will that depend on your emulator?
Yeah, that's a very good question. I think there might be 2 ways. So I think one way to validate that is to do sensitivity experiment directly use the emulator. For example, if the feature attribution detected impacts from, for example, like lower latitudes, impacts of the like integrated water vapor from lower latitudes, maybe you can like manually change the IWV over that region in the input and emulate and to see what is change in the output.
Mm-hmm.
And I think other way maybe I think using the climate module to do the sensitivity experiment will be much expensive to validate.
Yeah. Thanks.
I ask one or
We're
anytime.
gonna make it fast because I'm behind already.
Well, I was wondering about the relative cost of the emulator versus the interactive ice sheet. I mean, because that's the point of building the emulators, right? And then my other question is, have you looked at this in terms of Antarctica, and are you seeing similar features with the Antarctica sheet?
I haven't like looked at Antarctica yet, but I think there are similar work by other groups that they emulate the maybe surface mass balance over the Antarctic Peninsula only, but not the whole Antarctic ice sheet. Yeah, that's as far as I know. Thank you.
All right, I think I'm gonna cut us off. I just want to remind everybody online that if you have a question, you can raise your hand and we can call on you, because y'all have been a little quiet. Fine. And we'll move on to Miran.
Vizcaíno, very good.
Thank you.
So where is it better for the sound? From here?
Where would you like? So you can either you can sit where Gunter is, you can tell him to move slides, you can use your laptop.
I go do it. But can you put up another one that I put that says videos? So it's without the numbers. So there is another. So this is number 4 and there is one without number.
This one?
Yes. Yeah, that's better because there are a couple of videos. Super, thank you. Yeah, very happy to be here presenting this work with the coupled community system model version 2 and the community ICID model 2. So we are going to look here at the feedbacks between climate and ice sheet for Greenland in simulations where we completely melt this piece of ice. And okay, so a little bit as introduction. What Greenland is delivering at the moment to the oceans is equivalent to 0.7 millimeters of sea level rise per year for the global mean. And in addition to this impact, the ice sheet is a major tipping element. This tipping character is due to the feedback. So for instance, the albedo feedback more short term, and the elevation feedback in a longer term. And also to the shape of the ice, the hypsometry. So the relationship between area and elevation. So the ice sheet is like a plateau. So we have relatively a small area at low elevation where most of the melt is happening. But with warming, then the melt can move to higher elevations. And if the distribution of area increases very much because of this plateau shape, then this results in acceleration of the melt, just because of the shape. No? As for other roles in the system, the ice sheet is close to deep water formation regions. And we have also the opposite effect. So changes in the circulation of the North Atlantic affect the climate of the region where Greenland is. So there are two-way effects to be considered. Current projections are mostly based in ice sheet modeling with forcing from the output of global or, not ocean, global or regional climate models. There is, however, an ongoing effort within ISMIP, the ice sheet model intercomparison project, for air system models, including interactive ice sheet models. And it is targeting the comparison of two-way coupled simulations with one-way coupled simulations to isolate the effects of the coupling or the feedbacks and interactions on the air system and on Greenland. With CESM2, we have published simulations for the period 850 to 2100, also 1% to 4 times CO2 up to model year 350. There is a tipping study with CISM2 forced with CSM2, surface mass balance with elevation classes information. The main author of this one is Michele Petrini. And here what we are going to see is the extension of this published 1% to 4 times CO2 study, and in addition, a one-way coupled simulation for the same length of time. And with the comparison, we want to look at the role of mass and energy components on the mass loss, and also the role of the feedbacks by comparing the one-way and two-way simulations. Because we are looking at multi-century runs, from year 500, we went cheap, and we were applying a 5 times acceleration. So the climate year was, the climate component of 1 year was applied 5 years to the ice sheet, and then we were recoupling. Okay, so we have in the two-way couple case, the land component is calculating the surface mass balance and passing that to the ice sheet model. And the ice sheet model is gonna pass information of geometry to the atmosphere and also the land. And when we are retreating the ice sheet, we are exposing vegetation that we have prescribed from a BioMe simulation. And freshwater fluxes are, when they are liquid, they are provided from CLM, from the land model, and the ice discharge is provided from the ice sheet model. In the one-way run, we are going to prescribe the freshwater fluxes from a pre-industrial couple simulation. We take the climatology of the fluxes, and this is what we are imposing. Whatever CLM is calculating, then we rewrite it and we apply this pre-industrial meltwater liquid and also solid. And we fix the topography to the initial conditions that we have in the two-way couple run. So the two topographies are identical at the beginning of the simulation, and they start to diverge because they are evolving in the case of the two-way coupling. Okay, something went wrong with the figures. What can we do here? Okay, we don't have any figures.
Just give it a minute, they'll look.
It will come?
Yeah, so go
Okay,
back to
I
where
go
you're at
back.
and
Maybe
see.
it's because of the heavy videos.
Yeah. Do you see them
No,
on your screen?
maybe we can replace with it. Sorry?
Do you see them on your screen, or are they not loading
No.
at all? Okay, why don't you exit the presentation and see if they show up on the regular review? That's not good.
Maybe if she shares from her laptop.
Shall I
instead.
plug in my laptop?
Sure.
Yeah, just to try.
And your laptop too?
Yes.
I need to stop sharing from that one.
Yep.
And I do through here. So here. Down. No, it's not gonna.
Okay. Yeah, you might have to change some settings. Might be a little bit more complicated than what we can do now.
And directly, no, then it doesn't show up. And the number for presentation, maybe it works okay. The other one that,
Okay.
no, so they upload this whole.
Yeah, what about if we do this? Sorry about that.
Yeah, maybe we can see them at the breaker later today. You can show if anybody has questions. Sorry.
I don't know if this will be movies. Oh, yes, they are. Okay, so let's try this.
Okay.
Plan B. Like PowerPoint with thing.
Okay, I would like have, okay, so here you can see the evolution of global mean temperature. So this is the red line, okay? So by year 500 of simulation, we are at 8 degrees, more or less, of increase in temperatures. And here this year, we start with the 1 to 5 coupling, so you can see some transition there. This is the evolution of the volume of the ice sheet, and here you can see that we are losing the ice sheet after 1700 years. Okay, so if we are looking here at the evolution of the ice discharge, because we are not imposing ocean forcing at the outlet glaciers, the only effect that we see is that the ice discharge is going down because the ice sheet is thinning due to the melt. Okay, so the ice discharge is going down, and the ice sheet is becoming land terminating by year 300, more or less. No? And here you can see in gigatons per year the mass balance, which is the black line. Okay, so we have maximum sea level contribution around year 500, and then this goes down because the ice sheet becomes smaller and cannot produce so much input to the ocean. However, what we are going to see in the rest of the presentation is that I am scaling this mass metrics by the area of the ice sheet. So I am gonna, instead of gigatons per year, I am gonna be giving things in units of millimeter per year. So here you have the surface mass balance, not in gigatons, but in millimeters per year. Okay, so it's becoming very, very negative by the time the ice sheet is at 25% of volume. So this is a map of how it's a video of how the surface mass balance is evolving. So the blue parts are the accumulation area. The red parts are the ablation area. You can see how after year 200, this ablation area is expanding very quickly because of, among other things, these hypsometric effects of the shape of the ice sheet. And the margin that reacts faster at the beginning is the southwestern margin. We are losing now, by year 800, all of the southern part of the ice sheet. The northern part is retreating with a little bit of delay with respect to the southern margin, but it does eventually, as you can see here. And so by year 1300, we have only 20% left of the volume, and emotionally hard to see. Okay. Yeah, so here you have the topography. And this is the evolution of the velocity. So you are gonna see some, so you see decrease of the velocities at the margins as we are losing area, of course, and also thickness at the margin. So the velocities are gonna go down in the margins, but then more towards the interior, the velocities are gonna increase because the surface, the slope, is increasing. So here you can see the evolution of the slope, and you can see the reason why velocities have this increase in areas, for instance. Okay, so we are having now a very slow moving pile of ice by the end. Okay, so we have a story. We have this publication by Jonathan Gregory and colleagues that is suggesting that the retreat of the ice sheet is pulling the margin of high precipitation with the margin. So this can act to reduce mass loss rates because the precipitation is following the margin of the ice sheet. We are going to have a look at this. So this is the evolution of precipitation, and these are the anomalies with respect to the beginning. So we are going to see a decrease of precipitation here in the southwest once the ice sheet is retreating because we are losing this orographic forcing. And so if we look at the one-way simulation, this is how precipitation is increasing over the fixed ice sheet. Now, if we take out the effect of the precipitation accumulated over the area that we are losing, we have it here. And now we can isolate in the orange line is the difference between two-way and one-way over the common area, over the evolving area. So we can see that the precipitation change is increasing the amount of precipitation over Greenland. But when we look at the snowfall, that is what we care about, it's not the case. It is reducing the amount of snowfall over the ice sheet because the elevation decrease is increasing the ratio of rainfall over snowfall. Okay, looking at melt, now you can see here the evolution, and when we separate the elevation effect, what we are gonna see in the orange line is that as the elevation is going down and down and down, we have a very strong contribution of melt to the of elevation to the total melt. So when we have half of the ice sheet, 68% of the melt is because of the elevation change. And if we are looking at the sources for melt, this is the evolution of the melt energy in watts per square meter and the contributions from solar, long wave, and so on. So if we are looking to do percentages, so now it is with respect to 0, so to the initial values, we see that, so for instance, by half of the ice sheet, 37% of the melt is coming from solar input. I leave it here, 20% is this and this. And okay, so the conclusion is that albedo is key because it's supplying a lot of energy for the melt, and that the elevation feedback, we have quantified how much is giving to the total melt. And elevation is contributing negatively to the snowfall input. Yeah.
Okay. We are running a little behind, but do you have a quick question you want to say?
A quick one. When you melt back the ice sheets, you are replacing the land surface with vegetation.
Yes.
I'm wondering if you replace some area with lake, is that a realistic thing to assume?
The lake is only seen by the ice sheet model as water margin,
Okay.
but not by CLM. CLM is not seeing the lake.
Right, so next we have a quarter talk from Echo. Go ahead, sir. Hopefully we have it.
We do.
Oh, I get there.
Hello, good morning. I will start sharing my
Oh, we
slides.
have it, but the sound, let's see how the.
My name is Heiko Gölzer.
Did you record it on mute?
We can hear.
Presenting.
There it is. Okay.
It didn't like when I start sharing it. Okay.
Start sharing my slides.
Okay, I wonder if it's because we joined in as companion.
Yeah, I was gonna say it might be the companion issue. You know, we could put it after the break and ask Caitlin to see if we need to redo the audio during the break. So maybe we can move to
Oh,
Tim.
they could hear it online.
Oh, okay, well that's good. Oh, okay. Yeah, Tim, if you're around, maybe we can just skip to you for now, and then we'll do Heiko's talk after the break, and we can get him on the audio in the room. Hi, Tim.
I'm around. Hello.
Uh-oh. I don't have any audio. Maybe we need
Oh.
to turn the volume up on our speakers.
All right, I'll keep talking.
I don't know how to do that.
Should I keep talking, or will it be deaf if I do
Oh,
that?
no.
I am on the online call. Maybe it's one of us that's online can turn.
Sure. Oh. That was bad.
I will say.
Hey, Gunter,
So the microphones are working in the room, but not the audio.
I'm wondering if you can turn the volume up on the loaner laptop, just like the main volume instead of on the Google Meet.
It shouldn't be that, right?
Can't hear people
Can't hear anybody.
online
You can't hear
Yeah,
anyone on
I can
this?
still hear you.
talking and we can't
Oh.
hear him.
Can you hear me now?
Yeah, hold on.
Yeah, try like the main volume
Oh, and Daniel's trying to talk too.
on the Mac.
Yep.
Awesome.
Daniel's also online, so that doesn't. We should mime it.
Daniel, can you try to say something again?
Yeah,
Blah blah.
test.
Yeah,
Test,
we
test.
can't hear you. All right, we're gonna hang up, and then could you start the recording again?
Yeah, of course.
I don't know if you said yes or no.
Yeah, the recording.
Thumbs up.
Oh, there's, yeah.
Hello?
Hello.
Ah.
Thank you.
Actually, we might skip on the Tim and do the recording after that break, just because of the.
That sounds good.
Yeah,
Alright.
great. You can hear me now, right?
All right, now we can hear you.
Ah, great. Yeah. Then I'll. Can I safely share my screen, or will things break if I do that?
Go ahead and share your screen.
I will do so. There we go. You can see yourself right now, I think.
Yes.
You can now see a PowerPoint.
There's a PowerPoint.
Yep.
There is
You-
a PowerPoint. Great, there is a PowerPoint.
Yeah, you just have your little Google Meet window up. Could you
Oh yeah,
minimize that? Thank you.
there we go. Better.
Yeah, looks good.
Okay, great. Then then I'll just start. I think. Hello everybody from Stockholm right now, where it's dark outside. I will tell you a little bit about the latest paper that we have, or that's actually being typesetted right now, about including the present-day mass change rates in ice sheet modeling, and how it speeds up the ocean force modeled ice losses. So this will be a talk on the last chapter of my PhD thesis, actually. I've worked together with Bill and Gunther on this, and also with Willem Jan and Roderick from the Utrecht University. And our main purpose earlier was to develop a method that makes it able for ice sheet models to represent the present day observed mass change patterns correctly. And we were able to do so, and I've presented this a couple of times, and Bill as well. This worked very well. Like the SISM could reproduce the observed DHCT, the thickness change rates of the Antarctic ice sheet, almost exactly, like minus a little bit of model drift, but it's so minor that I will show that later that it doesn't influence the results at all. And well, the main conclusion from this developing of this method of the mass change rates was that in all cases that we tried back then, this led to an unforced West Antarctic ice sheet collapses. So if you would just give the ice sheet model the HCT rates of today, Thwaites Glacier and Pine Island Glacier on the Antarctic ice sheet would collapse, of which a typical 10,000 year realization you can see on the slide here. And that means that we have initialized the model with the mass change rates and then run it forward for 1,000 years, and then it looks like this typically, with a lot of ice lost on the West Antarctic ice sheet. So I'm first going to showcase a little bit about what this does to our initialization. So on the top you can see some metrics to showcase how good actually we think the initialization worked. Transient initialization means that we have included the mass change rates. Equilibrium initialization means that we did not include the mass change rates. We basically spun up to an equilibrium. And you can see the ice thickness bins on the modeled and the observed ice thickness bins on the x-axis, and the percentage of the grid cells that falls within these thickness bins on the y-axis. And the basically takeaway from this graph on the top of the slide is that our model setup is for both cases, for either if we are using the HCT or if we're not using the HCT, very well able to represent the present day ice sheet thickness of the Antarctic ice sheet. And down below you can see a zoom in of the Pine Island and Thwaites Glacier. And on the left you can see that's actually subfigure A. You can see the observed mass change rates, and in figure B and C you can see the modeled mass change rates of SISM. And in B it's after a single year of initialization, so you initialize it and then you run it for 1 year. And then in C you can see it for 5 years after the initialization, which you can see that the pattern of the mass change rates is pretty robust over at least the first couple of years of a SISM forward run. So we're actually, this is still kind of a proof to show that we were able to catch these mass change rates into the ice sheet model. And what I mentioned earlier is this is the model drift. That so if you just do the initialization and you don't do anything else, so you don't impose the mass change rates or whatever, this is what your ice sheet looks like after 1,000 years, with a thickness model drift rate of a couple of meters, with some spots like close to the grounding lines of, for example, Drilling Mountain, or here I think it's Abbott Ice Shelf where it thickens a little bit. So it's super stable. And you can see that in these graphs as well, where we plotted the global mean sea level rise, and also the ice volume above flotation percentage change over this model drift period. And you can see that for the whole Antarctic ice sheet, it changes with barely 0.5% over 1,000 years. So these simulations are, if you initialize them in this way, they're super stable. Then what we did is, this is what we call spaghetti plots. What we tried to do is we wanted to know what the effect of this initialization was on if you would include climate change. So all previous experiments were done without any warming, just with the present day forcing continued. But our main question here is, do we make the model more sensitive to ocean warming if we include the DHCT or not? And that's what we first tried to test with idealized warming scenarios, where we ramped up the ocean temperatures uniformly in the Amundsen Sea embayment with 0.2 degrees, 0.4 degrees, so with steps of 0.2 degrees until you hit 2 degrees Kelvin. Also to prove that the difference between the zero warming case and the zero warming case and the case where you will add a little bit of warming is different between the two initializations. Actually, this figure doesn't tell you a lot because I didn't label the lines correctly, but this figure will summarize a little bit better. these are the results of the idealized warming scenario. So from from zero warming until 2 uniform warming in the southern ocean warming in the Amazon Sea embayment. You can see at the beginning of the collapse, we defined this quite arbitrary, but as soon as like a certain ridge at which glacier is passed, you know that the glacier is going to collapse. The equilibrium initialization without the DHCT is actually a little bit more sensitive to ocean warming compared to the transient initialization. So actually the transient initialization where we add DHCT responds a little bit less with extra incremental warming compared to the equilibrium initialization. However, it's always below the equilibrium initialization. So in every simulation that you do, you will get an earlier collapse of the West Antarctic ice sheet if you include the DHCT patterns. And what I find personally very interesting is that although this seems to asymptote to a value that is well, maybe say 2100 or maybe 2050, the maximum global mean sea level rise rate from these experiments just keeps increasing linearly. And I suspect this is because we employ a grounding line melt scheme here that scales the best melting according to the percentage of the grid cell that is actually floating or grounded. So if you keep on adding more warming, you will also not only decrease the shelf size, but also take a little bit of mass away from the grounding line, which will, for high warming scenarios, also artificially decrease the amount of grounded ice that's sitting on the grounding line. But that's something that I couldn't confirm yet. So if you use if we shift away from the idealized warming scenarios and move towards the ESM force scenario, so we use the same Earth system model input as is being used for the ISNIP6 ensemble, and we force both the equilibrium initialization that's starting without the DHCT and the simulation starting with the DHCT with this ocean warming and atmospheric warming as well. And what we typically see is that it feels kind of obvious to say this, but it matters. It matters if you add your present day imbalance or not, and it matters for West Antarctic ice sheet collapse in such a way that if you add your DHCT to a realistically forced simulation of SISM, you'll speed up the West Antarctic ice sheet collapse by about 25 to 100 years, depending on how strong warming you're implementing in your model. And for the whole Antarctic ice sheet, actually, the difference in sea level rise becomes is quite small in the long term. So until 2500, the dashed lines and the solid lines are quite close together. But until 2100, it makes a big difference if you're included up to like 40 or 50% of your predicted sea level rise. Also big, and it's not only because the West Antarctic ice sheet is thickening, it's also because the thinning. It's also because some glaciers running outlet are thinning as well, or thickening as well. I'm confusing thickening and thinning now. I shouldn't do that too much. So but the main thing that I'm trying to say here is that on the short term until 2100, for all continental Antarctic ice sheet simulations, it matters a lot if you include your present day mass change rates or not. So the caveats of this, actually of the model that of SISM that we've been using right now, is that or opportunities for further research, actually a better optimistic way of framing what we're missing in the model, is that we're missing the subglacial hydrology connection here. So our basal friction field we use inversion to obtain it, but we keep it constant afterwards during a simulation. The same holds for the basal melt model. We also use inversion to compute an ocean temperature parameter to be able to give us the present day ice sheet, but we keep it fixed in the future simulation. That doesn't mean that the basal melt rate is fixed, but it means that the correction is fixed. And you would, of course, benefit from using a cavity resolving submodel or adding more physics into this single equation model that we're using right now. And of course, the calving is missing because the ice sheet front wasn't allowed to retreat through calving. It could only retreat if the basal melt would be so high that the complete shelf would be gone. But we did some initial tests together with Bill and Gunther with stress-based calving, and to see if we can get the stable like a stable model of ice sheet from that. And for some cases we could, not for all cases. So it's quite volatile if you include stress-based calving into SISM. But it speeds up the collapse even a little bit more. And we tested this with like a no ESM run and with some of the Earth system models that were selected for the ISMIP6 ensemble. We couldn't do it with all of them because the model would just give a crash. To summarize it, yeah, the model would crash if you gave it certain ESM forcings. And also, what I would like to share with you today is that I'm moving away from the Antarctic ice sheet. I'm a Greenland modeler now, and I also don't really dare to say it, but I switch models. I'm using ISSM right now, so I was really happy to hear the first talk about that I'm not the only ISSM modeler in the room. It's a beautiful model in its own way. Let's put it politically correct. It uses data assimilation and cost functions, and that is something that I haven't used before. And I will be applying it on the Northern Greenland outlet glacier. So if you're an ice sheet modeler or you have experience with this kind of modeling, then please feel free to contact and we can have a chat, and maybe we'll both learn something from that. So with that, thanks for your attention. Yeah, the paper about this is being typesetted right now. And if you have any questions, I'll be happy to answer them here, or you can, you can contact me.
Vicky, Charlie?
Let me stop sharing.
All right. Do we have a quick question in the room for Tim? Like, why did he go to ISSM? There's a story. It's fine.
I had no choice.
Okay.
Everybody else at the department here is using ISSM, and I can share some. I mean, I shouldn't. I actually, for now, I like SysM more because I'm used to it, and now I'm learning ISSM, so I'm like bumping into different caveats that I'm not able to solve yet. The beauty with ISSM is that it's out of the box usable, and I can run it on my own computer because it has grid refinements and a triangular mesh. It's super efficient, but the bad thing about ISSM is that it's been built with MATLAB bindings, and that you can. It's easy to like get it going and actually get it initialized to do something. But if you want to do something else, you want to change the friction law, you want to play around with the Kelvin laws whatsoever, it's much harder to do that than it is in SysM. SysM is very, and that's a compliment to all of you. It's very well documented and really easy to maneuver through if you're a new modeler. You want to know like, oh, I want to change something in the friction, or I want to add the friction law. Oh, that's happening in this file. I have to change this or something. So that's the good thing about SysM, I would say.
That's awesome. Very, very good feedback. Thank you, Kim. All right, so we could play Heiko's presentation real quick and just go to the break a little bit late. I don't know if there's a desperate need for restroom or anything in the room. Okay, let's go ahead and play Heiko's.
It wouldn't take me with Heiko is recording. You might want to ask a question, but you won't get an answer. So
yeah, we can just go straight to break after this.
if it works.
Hello, good morning. I will start sharing my slides. My name is Heiko Gölzer, and I'm presenting work produced as part of the European project PROTECT, which is titled Extending the Range and Reach of Physically Based Greenland Ice Sheet Sea Level Projections. My co-authors on this work are mainly people that have produced climate model forcing for our experiments and other ice sheet modelers like me. We present an ensemble of physically based ice sheet model projections for the Greenland ice sheet. Our ice sheet model simulations are forced by high-resolution regional climate model output and other climate model forcing, including a parameterization for the retreat of marine terminating outlet glaciers. The experimental design builds on the protocol of the ice sheet model intercomparison project for CMIP6, and extends it to more fully account for uncertainties in sea level projections. We include a wide range of CMIP6 climate model output, more climate change scenarios, several climate downscaling approaches, a wider range of sensitivity to ocean forcing, and we extend projections beyond the year 2100 up to year 2300, including idealized overshoot scenarios. With this slide, I want to show how our work fits into the ongoing ISMIP cycles. The ice sheet model intercomparison project's core activity is to design and deliver the projections of the sea level contribution of the ice sheets. ISMIP 6 started already in 2014, and mostly ended with providing input for IPCC AR6 in 2020. And in terms of the projections, the European project PROTECT was planned as an interim follow-on from ISMIP6 and extended the projections in several ways. Some of the developments of the project are now informing ISMIP7, which is actively working towards the IPCC AR7 fast-track delivery. So this is also why we are using an experimental setup which is very closely aligned with ISMIP6, and that is described here. We use global forcing from selected CMIP climate models, which represent climate change over and surrounding the ice sheets. This is then downscaled with regional models to the ice sheet scale and complemented with parameterizations as described on the next slide. Finally, we are producing projections with standalone ice sheet models that consider the ice sheet evolution along with associated uncertainty. The slide gives a bit more detail about the forcing. The surface mass balance forcing is provided as anomalies relative to the 30-year period 1960 to 1989. And we are also providing data to parameterize the surface mass balance elevation feedback. For marine terminating outlet glaciers, we are prescribing the retreat with a parameterization, which is empirically derived and using ocean temperature and runoff from the ice sheet. The parameterization includes a sensitivity parameter called kappa that is used to sample the uncertainty in this approach. The forcing available to the ice sheet modelers is illustrated here with a few examples. On the left-hand side, you can see the surface mass balance anomaly for a number of different climate models and scenarios. It is typically decreasing over time as the climate warms and melt and runoff increase. The panel in the middle shows an example of the surface mass balance anomaly field at the end of the 21st century for one of the models, where you can see strongly negative anomalies over the margin of the ice sheet. And on the right-hand side are examples of the projected retreat that is imposed on marine terminating outlet glaciers, which can be several kilometers by the end of the 21st century. I will now go on to describe the ensemble setup and the initialization of the ice sheet models. The slide gives an overview of the ensemble, and here you can see on the right-hand side a schematic that combines the different forcings and modeling choices that constitute one specific ice sheet simulation. And on the left-hand side, you can see all the possible choices for these different components and forcings. Altogether, we have produced almost 1,500 individual ice sheet model projections that form the basis of our results. The number of participating ice sheet models was limited here to those available to the project participants, namely 4. However, each ice sheet model was run with several variants, e.g., for example, for different resolution, for different sliding law, or different approximations to the force balance. A large part of the experiments and all the extensions to 2300 were performed with the community ice sheet model, CISM, here in green. All 4 ice sheet models use different initialization approaches, with EMO-ICE using a paleoclimate spin-up, while the other 3 models used various ways to calibrate the basal friction coefficients. The figure shows the mismatch with observed ice thickness at the present day and is ordered left to right by decreasing root mean square error. And with this, we are now ready to look at the results of the projections. Here we're looking at a subset of experiments with 1 model variant per group and using only the forcings that were specifically produced for PROTECT. This is to give a rough overview of the typical range of results and the time evolution of the sea level contribution from the Greenland ice sheet from 1960 to the end of the 21st century. As an important step forward from ISMIP-6, 3 of the ice sheet models are forced with realistic retreating outlet glaciers over the historical period, which helps to get ice sheet mass changes better in line with the observations. And compared to ISMIP-6, we have less ice sheet models, but more variants to compare, as mentioned before. Here's an overview of the sea level contribution in the year 2100 for all available simulations, with the total range from 16 millimeters to 354 millimeters. The highest numbers are from experiments with extreme retreat forcing, shown here with green triangles. An important addition compared to ISMIP-6 is that we have 2 additional regional climate models, where there was only 1 regional climate model used for downscaling before. It is now generally recognized that this is an important source of uncertainty that needs to be better captured. We've also added a new intermediate scenario where we only had the extreme scenarios SSP 126 and SSP 585 before. And we have also additional CMIP models and cover a larger range of the uncertainty in the ocean forcing. Now turning to the simulations going to the year 2300, where Greenland simulations in ISMIP-6 ended in 2100. Not many of the CMIP results that are available and useful for regional downscaling extend to the year 2300. And we have therefore only a very few sample of what we call natural scenario MIP extensions to the year 2300. And these are shown here in panel C. For those experiments where we only have the extreme low and high scenario SSP 126 and SSP 585, global warming levels are either around 2 degrees for the low SSP 126 in purple, or more than 13 degrees in green and orange for SSP 585. The resulting ice sheet response is equally extreme for those scenarios with 2 to 3 meter sea level contribution by 2300 for the high SSP 585. And in these cases, the ice sheet is losing a considerable part of its mass. To complement these experiments and filling the gap in between, we have schematically constructed additional scenarios, which are shown here. One example is extensions to 2300 based on existing forcing, where we have constructed overshoot forcing mimicking the scenario SSP 5.3.4 overshoot. We can see that the response depends on the underlying Earth system model, but also shows that for a third of the experiment, the ice sheet may be stabilized. Using another approach, we have repeated forcing from the end of the 21st century until 2300 shown here. It shows that the ice sheet response is strongly dependent on the scenario and on the climate model choice. And so to summarize the extensions to the year 2300 here in one figure, we find the largest contributions for natural extensions of extreme scenario SSP 585 going up to 3 meters. We find that the ice sheet may be stabilized for some of the overshoot scenarios, and repeated forcing from 2100 shows large dependence on scenario and climate model choice. And with this, I would like to thank you very much for your attention. If you're interested in this work, you can check out the paper linked here. Thank you very much.
All right. Well, I can't answer questions, but I'm sure you can contact Heiko if you need to. Thank you, everybody. Let's go to break. She's back at 10:30 for the second.
So welcome back, everyone. I'm taking from Kate the time watching responsibility, and I'm going to introduce the first speaker after the break, who is Anne-Sophie Singh, and she's going to present the results from her PhD research. So go ahead, please.
Yes, thank you. Let me just share the screen and oops. There. Is it looking okay for you?
Yeah.
Perfect. Thank you very much. So yes, my name is Anne-Sophie and I am a postdoc at the University of Copenhagen, but today I'm presenting work from my PhD that I did in Miren's group in Delft. And the presentation today is titled Channelized Melts Beneath Antarctic Ice Shelves Previously Underestimated. And the reason that we study ice shelves and the reason why we study the basal melting of the ice shelves is that ice sheet instability processes such as basal melting of the ice shelves are some of the main contributors to uncertainties in sea level rise projections. So if you want to reduce this uncertainty, we need to understand some of these processes better. And it's not just basal melting, but it's also channelized basal melting, because these basal channels, they represent potential weak zones on the ice shelves. And here is an example of Pine Island Glacier, and this is a satellite image from 1982. And the black arrow here points out a channel on the ice shelf. And if we move through time, then we can see that this channel becomes more and more pronounced. It becomes thinner, and we also see fracturing occurring, and fracturing both along and across the channel, and that the ice shelf front retreats along this channel when we move through time. So this is an example of how these basal channels, they represent potential weak zones on the ice shelves. Now, I am not a modeler, which I assume that most of you here are, but I do remote sensing. And when we from remote sensing want to estimate the basal melt rate of an ice shelf, we all use more or less the same approach. And this was a part of the first part of my PhD was to develop a method to do this. And I did that, and it was called BERGI, and it's basal melt rates using REMA and Google Earth Engine. And we all use the same equation, which basically just says that some ice thickness change of the ice shelf has to be explained by the ice flux divergence, the surface mass balance, and the basal melt rate. And the surface mass balance, we get that from models. The ice velocity for the ice flux divergence, we get that from remote sensing data. And then it comes to the ice thickness and the change thereof. Well, from satellites, we can measure the elevation of the ice shelves, and if we measure it at one point in time, but also at a later point in time, then we can calculate the Lagrangian difference between the two. And then when we assume hydrostatic equilibrium, then we can translate this surface elevation into an ice thickness. And it's the same approach which all remote sensing products they use. It's all based on this equation. Now, I applied this method to some of the most vulnerable ice shelves in Antarctica, and I know that there are a lot of things going on here, so I will instead just zoom in on a few ice shelves. And here to the left, we can see the BERGI basal melt rates, and to the right, we can see those of Addis Amelia et al. From 2020. Now, the difference between these two products is the surface elevation data which they use, and Addis Amelia to the right makes use of Cryosat-2 satellite data. It's radar altimetry data, where I use a combination of different satellite products. And what we can see is that when I use this combination of different satellite products, then we get much greater detail, much greater spatial resolution of the basal melt maps. And as mentioned, the reason for that is the surface elevation product which we use. Here you can see that the plot where it says REMA and TOP that's a kind of the surface elevation data which I have used, and it has a lot has a much better spatial detail than the Cryostat-2 elevations to the right. But it's not just the spatial resolution which is better, but when Cryostat-2 measures the surface elevation of an ice shelf, it measures the point of closest approach to the satellite, which means that low-lying areas that are surrounded by higher terrain, they will remain unseen to the satellite. And that's what we can really see here, where this is a Totten ice shelf, and you can see that many of these channels that are present in the RIMA elevations, they are simply gone in the Cryostat-2 POC elevations. And to the left, where you can see the basal melt rates with the Cryostat-2 measurement points on top, you can also see that also corresponds to some of the areas where there's simply no basal melt rates for that product. So the reason why we get the higher detail is because of the surface elevation data that we use. This is a bit of a complicated figure, and I usually don't include it, but because it's more of a modeling community here, then I just want to mention that we did a Fourier analysis of some different basal melt maps, basically just to figure out if there was a specific wavelength, or what interesting wavelengths there are at which basal melting happens. And what we could see is that there is this lower characteristic wavelength of 500 meters at which basal melting happens. So think of that maybe as the channel width, and that is the resolution which models should be able to capture in order to capture channelized melting. And what we also show in this figure here is that actually Bergy is the only of these three products which we compare that actually explores this full, all of the frequencies, all of the wavelengths at which basal melting occurs. We also look into the distribution. So we compare three different products. In gray, we have the Addison-Mealy that I showed you before, so that's the low resolution. We have the product from Davison, which is, they also make use of Cryostat-2 Cryostat-2 measurements, but processed in a different way, which allows for slightly higher spatial resolution. And then we compare that to our Bergy results in green. And here we look at the melt rate distributions within different ice thicknesses. So what we can see here, for instance, in panel A, is here we take all of the parts of the ice shelves that have an ice thickness from 0 to 200 meters, and we plot the melt rates. And then the next one is from 200 to 400 meters, and so on and so forth. And what we can see is that for all ice shelf sections that are thinner than 1,000 meters, Bergy has higher median melt rates. And that is quite important because these thinner ice shelf areas, or the areas where the thinner ice shelf areas is usually where we find channels. So we also map out channels on all of the ice shelves. And here we also compare to the thickness, especially on Dodson ice shelf. You can see how these channels, they also align with, of course, thinner ice. But we study those channels that have the highest melt rates because we consider those kind of the active channels. And when we do that, when we study, then we take the peak melt rate within the channel that can be thought of as the maximum melt rate that is within a channel. So that's what we have on the x-axis here. And then on the y-axis, we have the ice thickness. Then all of the different shaped dots, they represent different channels on different ice shelves. And what you can see here is that all of the green dots, so that's all of the Bergy, that's all of the channel, the melt rates based on Bergy. Those peak melt rates, they are far higher than for the other two products. So we have so the melt rate that we get within the channels is higher than the other products, and it's actually up to 50% higher. So the other products, they simply underestimate the melt rate within the channels. And because they underestimate, we also want to know, okay, so what might that have of an impact on on channel vulnerability or ice shelf vulnerability if you use those melt rates to make assumptions about that. So to do that, we calculate the breakthrough time, or we look at the breakthrough time, so the time that it takes for a channel to break through the ice shelf. What some people have done previously is that they just take the linear incision line. So if you have an ice shelf that's 100 meters thick and has a melt rate of 10 meters per year, then it should take 10 years. But that is not the case, because we need to take secondary flow into consideration. So that is the fact that the ice will try to close up these channels. So what I have plotted here is the case for a low melting scenario. So in a case where there's relatively little melt, then these channels, they can simply just sustain. If we now turn a bit up on the melting, how much it's melting, then it looks like this. And in the case of high melting, then the linear incision rate and the secondary flow breakthrough rate, they are almost similar. So it takes almost, so it's, you can almost assume that it's a linear incision. And you can really see that it depends on the melt rate within the channel. And this can also be put into this phase space here, where we can see the more, so that's the normalized breakthrough time. So that's the secondary flow breakthrough times normalized by the linear breakthrough time. And the more blue it is, the closer we are to the linear breakthrough time. And what you can see also that for higher peak melt rates in general, we are closer to the linear breakthrough time. There is also this line here around 400 meters, where if your ice shelf is thinner than 400 meters, then in that case, a linear breakthrough time is actually a quite good assumption, and the secondary flow cannot really battle with that. So we also put all of our channels into this phase space where we can really see what this means, because we have all of the green birch here. I've zoomed in on a smaller area just. And here we can see how all of these green dots, they are much more located in the blue and greenish areas than the other dots. And many of the channels that might not, like for instance for Davison or Addison-Mealy in gray and yellow, they are located in the part of the plot that's just white, which is because it's below, that there's melting below 8 meters per year. And if that's the case, then the channel cannot break through, it can simply just sustain. And what we can see here is that the birchy melt rates also lead to a lot faster channel breakthrough than for the other products. So here I've just chosen some selected conclusions, is that birchy, which uses a combination of stereoimetry, REBA, with radar altimetry, leads to, or allow for basal melt mapping of high spatial resolution. And that basal melt products that rely solely on radar altimetry, they underestimate channel melt rates by up to 50%. Note for modelers is that in order to capitalize channelized melting models, they need to resolve basal melting down to 500 meters, or at least the implications thereof. Now, before I end off, I also want to advertise a bit for another paper where birchy has revealed the formation of new channels. So I just want to take a short trip to George VI ice shelf. And here we can see the surface elevation from 2012 and 13 of a very small part of the ice shelf, but there you can see a kind of a funky looking channel. And if we move through time, nothing much happens to this channel until about now. And if I just skip a few steps ahead, then now we can see that a new channel has started to form. And it becomes deeper and deeper through time. And if we look at a cross section, then we can see the old channel, the one that was originally, is closing up, while this new channel is opening up. And this happens, the onset of this of the formation of this new channel coincides with a very strong El Nino event, which also led to a speed up of the glaciers feeding into George VI ice shelf. So this is just to show how these basal channels, they can do a lot of weird and funky stuff. So with that, I would like to say thank you, and I'm open for questions.
Many thanks, Sophie. Do we have
Thanks. That's a great talk. So you mentioned in Virginia you use the flotation condition to model ice shelves. How big of an assumption is this? Because is it for like discovering those channels? Because I would say that when you start melting, when you use flotation condition and then you start channelizing those melts, then this assumption is broken at least for some time. Do you have any idea on like how long this assumption can be broken for, or how long it lasts, or like the
Yeah,
impact?
so the biggest problem when it comes to the hydrostatic assumption is near the grounding line. That's where we have the biggest problem, because of course it's not immediately floating in the hydrostatic equilibrium. So that's where we have the biggest issue. There is also some bridging stresses acting across channels. And I know that my co-author Martin Wearing, he looked into that in his older papers, and it's I don't remember the exact numbers, but the effect of those bridging stresses, or like, yeah, in terms of the hydrostatic equilibrium across the channels, is relatively small. But I don't remember the exact numbers. But the biggest problem is for sure near the grounding zones, where all basal melt products based on satellite imagery, they should really be used with care. Yeah.
Yes, Richard.
Is laser altimetry useful for basal melt mapping, or does that have its own issues?
Laser altimetry is very good as a supplement to. Well, I think one of it's not good to just rely on one satellite product. I think that the best is to combine a lot of different products, because satellite or laser altimetry is definitely good because it really measures you would get the channels and everything, but the spatial resolution, like to cover an entire ice shelf, that would be difficult. So the spatial resolution which you would obtain if you just use laser altimetry alone is not the best. But if you combined it with some of the other satellite products, then you can really do something. Then I'm sure you can do something really cool with that.
Thank you.
Well, one more question for you, and it's about your third bullet point here. So modelers and observationalists need to talk a little bit more so as to understand each other. And while I fully understand why you put this high resolution need to capture those better channel, and right now, when it comes to CISM, unless you find a way to run it regionally, it's hard to run at this high of a resolution for the full Antarctic ice sheet like we typically do. So based on your experience, imagine what we use as a 4-kilometer uniform grid for this. Would you have any recommendation, given the resolution, there's a coarser resolution we run at if we want to make the best use of your product?
Mm.
And I know I put you on the spot, and
Yeah.
it's a discussion topic that we might have also like later. But I think
Yeah,
it's also an area where both crew need to interact more.
So it's more or less only on the Dodson ice shelf where you have a channel that is wide enough to be captured in that 4-kilometer resolution. But of course, most of the melting takes place, or the highest melt rates are found near the grounding lines. But I don't know, I don't really have an answer to, if you stick to if you have the 4 kilometer resolution, then I'm not sure how you would be able to model the impact of the channels, because the channels, they can both stabilize and destabilize the ice shelves, because they can stabilize in the way that you can distribute the melt in ways that are beneficial, or the channels, they can interact with fractures and so on and so forth, and thereby cause instability. I don't know. Really, I think probably regional setups higher. I guess probably regional setups of higher spatial resolution, where you're able to tackle some of these questions and then see whether it matters if you do it on a global scale, I guess.
Thanks.
We are going to move to the next speaker, who is Trevor. I believe he's online.
Yeah.
Yes. Hi, Trevor. Go ahead.
All right, let me get screen sharing going. Does that work okay?
Yeah.
Okay. So yeah, I'm Trevor Hillebrand. I'm at Los Alamos National Lab, and I'm a developer of the MPAS Albany Land Ice, or MALI, ice sheet model. And Gunter asked me to talk today about our initialization approach for our Antarctic ice sheet configuration that we used for ISMIP 6. This animation here is one of the high-end or high emissions, I think, plus hydrofracture scenarios for ISMIP 6. And I'm not really going to be talking about these projections today, and mostly talking about our working towards our initial condition. And the reason I have this is because many of the figures you'll see today are things that I had to dig up from notes that are 3 or 4 years old. And so you're going to see a mix of publication quality figures in this preprint on the bottom right, and basically thumbnail quality figures that I had to dig out of very old documents. So here is this is just an overview of our configuration. So MALI is a 3D bladder pattern based model with thermomechanical coupling by a temperature-based thermal solver. And we have a 4 to 20 kilometer variable resolution mesh. It's about 400,000 cells in 5 vertical layers of varying thickness, with terrain following signal coordinate. And so basically the whole talk today is going to be about how we get from these observed velocities to this modeled initial condition shown here that gives us a reasonable hindcasting or historical behavior. So we use a nonlinear Weertman type sliding law with an exponent of 1/5 rather than the typical 1/3. And this was done by a small set of tuning experiments shown in the bottom here. So I will get to that in a bit. And we optimize our basal friction and ice stiffness fields to get from panel A in the top to panel B, but there's a lot of other ad hoc steps that we're going to talk about today. So just a quick overview of our historical runs here. So this exponent of 1/5 is this solid curve here. And you can see that this actually doesn't give us the best fit to the continent-wide observations from the Regnault data set. But the reason we chose that is that it gives us the best fit in the Amundsen Sea to the observed mass change. So we accept a bias overall across the whole continent in exchange for doing a much better job of matching observations in the Amundsen Sea in this purple band in the middle here. And then this panel on the bottom right shows our historical simulation. There's black curve, so we have a slight positive trend in mass change. We gain about 1 to 2 millimeters of sea level equivalent over the historical period, compared with these observations showing a few millimeters of mass loss, or a few millimeters sea level equivalent mass loss over that period. And then all the other ISMIP 6 models are shown in these gray curves. So we have a slight positive bias. We're doing better than a lot of these models and worse than a handful. So we're kind of in the middle of the pack there. And so, yeah, running this configuration forward under these different forcings provided by ISMIP 6 puts us in this range here. In this orange bar in the right-hand panel is the MAHLI 4-kilometer simulations. So we're once again kind of in the middle of the pack, skewed a little bit more towards more mass loss than many of these other models. But I'm not really talking about this today. I'm talking about how we get to time 0 here on this plot. So we start with a PDE constrained optimization. So we have this adjoint inverse solver that will solve for the basal friction and ice stiffness fields that'll minimize the misfit of our modeled velocity to the observed velocities. And so we have this composite observational data set of velocities on the left. We solve for these fields that give us a surface velocity on the right that minimizes that misfit. And it's important to note here that we can solve jointly for temperature, but we ran into just solver convergence issues on this mesh, and so we use the temperature field from a previous inversion on our 8-kilometer mesh. And since I talked about tuning this the friction lot exponent, we can do this optimization once for the friction coefficient, and then for different assumptions of the value of the exponent, we can recalculate our friction field, so we don't have to redo this expensive optimization just to use a different exponent of that sliding law. Okay, so yeah, we have this optimized surface velocity based on these fields in the middle here that give us a decent match to observations from this composite data set, but this doesn't give you any guarantees about how this will behave in forward simulations, right? So what we found when we started running this forward, and this is where we get into the figures taken from deep in my notes, is, so let's look at this main large panel here. This is a run with historical forcing. Let's just look at the dark blue curves here. If we just run that initial condition forward, or run forward from that initial condition under historical forcing, we get this huge mass gain. And our grounding lines are advancing like crazy everywhere, or most places. So looking at the Philips-Shirani and Ross sectors, these panels on the left, just comparing these black curves, which are the total mass change, to the gray shaded regions, which are observations. You know, we're gaining a ton of mass in these regions relative to observations. But we realized that that the uncertainty in the bed machine data product under these large ice shelves is really high. It's on the order of 100 meters. And so just making relatively small changes to the seafloor elevation under the ice shelves has a large impact. So these different dotted, dashed, and dashed dot curves here are just dropping the seafloor under those large ice shelves by 5, 10, and 20 meters, respectively. And so we dropped the seafloor under the large ice shelves where there's high uncertainty by 20 meters, which hugely alleviates this mass gain problem. But it actually makes the problem, our bias, worse in the Amundsen Sea because we were losing too much mass there already. And so we lowered the seafloor everywhere by 20 meters, except in the Amundsen Sea, where that made our problem worse. We also we continued to have grounding line advance in parts of the Philips-Shirani, and looking closely at bed machine, especially in these troughs in the cyan box here. We saw that there's like a jump in the bed elevation across the grounding line. So this is like clearly a data interpolation artifact. And it was just causing massive grounding line advance, no matter what we tried. And so lowering the bed there by 20 meters didn't have a large enough impact. And so we sort of manually excavated or bulldozed these troughs to create a smooth transition in bed elevation across the grounding line. So here's a zoom in this bottom, in this right-hand panel here of these troughs. And that, in the regional sense, really decreased our mass gain. We still have a positive transient there by the end of the simulation, but it's much smaller. And that was most of that signal in the whole ice sheet on the top panel here. We also had to do some heavy excavation of this trough under the Brunt ice shelf, but that didn't actually have that large of an impact on the forward behavior. Okay. We also noticed that, so I mentioned before that we were losing too much mass in the Amundsen Sea. And we noticed that interpolating from the high resolution bed machine product to our 4-kilometer resolution mesh smoothed out the geometry enough that we lost the pinning point in Thwaites ice shelf. And so we raised the bed under the ice shelf to reestablish that connection to about 40 meters thickness above flotation in line with observations. We had high hopes for this as a way of alleviating that grounding line retreat, but if you compare the solid curve before the pinning point and the dotted curve after adding that pinning point with the gray curve from observations, that really doesn't go a long way towards alleviating our problem. So at this point, we tried everything we could think of. We increased the friction, basal friction in this area. We increased ice stiffness. We tried removing the western ice tongue because that seemed to be like dragging the eastern ice shelf along because weren't running with active damage solver. None of these things helped, and we still kept getting this massive retreat in the Amundsen Sea. But when we took a step back and thought about this, the bed machine ice thickness is nominally a 2015 product because it's based on REMA. And if marine ice sheet instability is indeed underway or has been underway for a few decades, we realized we might be kind of baking in instability just in the geometry by starting with a 2015 product. And then any discrepancies between our modeled and the observed velocity fields could be exacerbating that. And so what we tried was using ice thickness derived from a BedMap2 ice surface. So the DEM was like early 2000s, something like 2003. And then the bed machine version 2 bed, which should be much higher quality than BedMap2. And so this gives us kind of an early 2000s kind of ice geometry. And this went a very long way towards alleviating that bias. So this dotted curve here is the same as the dotted curve on the left, and then the solid curve is after changing to the BedMap2 geometry. And so we're still kind of hugging the very bottom edge of that of those observational bounds, but we're within or at least adjacent to the observational constraints. Okay, so to summarize sort of our total initialization workflow, we start with this optimization for our basal friction and ice stiffness fields to match the observed surface velocity. And then there's this whole list of kind of ad hoc steps that we had to do to get our historical behavior in line with observations. And so that was lowering the bed topography below ice shelves where those numbers are uncertain to combat grounding line advance, removing some interpolation artifacts downstream of the grounding line in ice stream troughs where that advance was most egregious. We added back that pinning point to the Thwaites ice shelf, and we used BedMap2 derived ice thickness in the Amundsen Sea. And then after all of this, we ran a short 10-year relaxation run with zero melting in the Amundsen Sea to remove fast transients in the ice sheet without causing too much grounding line retreat in the Amundsen before our initial condition. And then finally, at this stage, we're actually ready to do these tuning runs for the basal friction law exponent. Okay, so that's our ISMIP6 configuration. That preprint I linked to on the title slide has a lot more details about that, as well as many sensitivity tests and an ensemble of simulations and analysis of variance. So if you're interested, I encourage you to check that out. But now, of course, we're moving towards ISMIP7 and everything's going to change. So these are our anticipated changes. This might be slightly aspirational, but we're looking at moving towards higher resolution, potentially down to 1 kilometer maximum resolution, or maybe 2. Obviously updating from the BedMachine version 2 to either BedMachine 4 or BedMap3. And then instead of just a velocity constrained optimization for our initial condition, we're planning to incorporate DHGT constraints, and I think that should go a long way towards alleviating a lot of these issues with the historical behavior that we had with our previous mesh. We've recently implemented higher order schemes for advection and time stepping, so we'll be moving from first order to higher order, as well as trying to run with dynamic stress-based capping laws that are currently implemented in Mali, but we were unable to calibrate in the time frame for ISMIP6. Moving from a power law Weertman friction to regularized Coulomb, and adding coupling to a global sea level model that Holly Hahn coupled to Mali. Things that are staying the same, probably sticking with our bladder pattern velocity solver, although we do have a new depth integrated sort of mole style solver, which is about a third the cost. Using thermomechanical coupling based on the temperature solver, sticking with the typical quadratic non-local subshelf melt parameterization, as well as this quasi-linear melt for grounded termini. And I think I'm probably at time, so I'll stop there and have any questions.
Any questions? Any questions online? Yeah, continue.
Hey Trevor, thanks. Great talk. I was wondering, in the first place, why did you choose the bathymetry from BedMachine 2 as opposed to BedMachine 3? Because there are like strong differences even for Swait. And like, how would do you know if it would have any impact on your neutralization procedure and your future runs?
Right. The reason for that was just that we didn't have BedMachine 3 in hand at the time we started this mesh. So, yeah. So we haven't tested with updating to BedMachine 3. Yeah, I have no insights into how that would impact it. One thing I have looked at is the difference between BedMachine 3 and BedMap3. I haven't done this for BedMachine 4 yet. But BedMap 3 looks like it has a lot more realistic kind of small scale roughness in the bed in the Amundsen Sea. So that'll be interesting to see if that has an impact.
Kate, please. I have a quick question about the DIA that you're adding in here. Would you see that having a stabilizing effect on these scales? Or is it more about the long-term simulations that you're adding that in for?
On these scales, meaning over the historical period?
Well, yeah.
It would have a small impact over the historical period, but over the multi-century period. Holly published a paper last year with our ISMIP6 configuration coupled to the sea level model, and it's like up to 50% decrease in mass loss for the very strong forcing scenarios.
We are gonna move to the next speaker. It's
me?
Yes.
Oh, I thought Gunter was going with me. All right, speech over. Okay. So, oh, I am in front of that. And then, so how do I just share this for you? Great. Hi, everybody. I'm Kate Bear-Calder. I'm the software engineering liaison for the Landice working group. So I'm just going to give sort of a quick overview of the software engineering work that we've been doing recently. And by recently, I'm including basically all of last year because that's the SISM 2.2 release. This is the basic slide for the new in-car rebrand. It had this really pretty storm system over the Northeast US, and I was like looking at the snow and thinking about how nice that would be in Colorado. So one of the problems with software engineering talks is that I don't have pretty plots or, you know, cool pictures of ice to talk about. So I usually try to bring in some kind of a funny meme or generated pictures. And this year I'm just going to show pictures of snow from previous winters to remind everybody this is something. And hopefully it will be a little bit of a snow dance and we can bring in some snow to Colorado. So topics I'm going to talk about here real quick are the Docker build that we have for SISM right now. I'm going to give an overview of some work we did with the topography updating script. I'm going to talk about some of the SISM updates that we've done for the main core SISM code as we bring it into CESM, and the name list and CESM changes that were required to support those. One of the specific things I want to talk about is the exact restarts and changing processor counts, which is coming up right now, and we're very excited about. And adding in support for the Data Glacier and SISM Wrapper. And then finally, the last two topics here are going to be an overview of future projects. So we're talking about bringing in a global solid Earth model mantle convection as part of CESM components, and that's pretty exciting. And then Zheng has been started a whole new project on isotopes, and so we're going to have a quick talk about that at the end of this. So this is something that's available for SISM now, but it hasn't been fully documented, and we're still like testing. But Docker is a piece of software that lets you run containers on any computer, for instance, on your laptop. And when you start this container, you have an environment available that looks just like any other supercomputer, as far as the libraries and the Python and everything else that is set up for that. So we have a container available now that you can install SISM into and run on your laptop, which lets you run locally with very few steps. It's not a big parallel machine. It doesn't have like the PBS queues that you would get on a big supercomputer. You're still using the same processor on your laptop that you would normally. But if you're running a simplified version or a low resolution version of SISM, it does just fine. So it's a nice quick way to get SISM running on a new machine. So feel free to contact me if you're interested in playing around with that at all. I think the documentation for this will be involved in this SISM 3 release as well. So similarly, this is a snow on the mesa. Last summer, we had a summer intern from University of Connecticut. She's actually an undergraduate intern with the CI Compass, so Cyber Infrastructure Program. And she used the Claude AI tools to develop a Python-based version of our topography updating script. So in the past, in order to couple the ice sheet to the atmosphere, we have to run offline code that adjusts the surface topography of the atmosphere to represent the changes in the ice sheet. And this has been a little bit of it was a very forward-thinking tool when it was built. It includes Bash, NCL, and Fortran all together to create these topography updates. As the machine libraries change and CSM changes, it tends to break out from underneath us. So Tamara managed to build a version of it entirely in Python. So that's a really good first step. It means that we have the ability to build on that infrastructure in a way that's more sustainable going forward. So this is something that we're hoping to use for the CMIP forward runs. It doesn't necessarily need to happen for the spin up or the pre-industrial runs for CSM3. And it still needs to be adjusted for the unstructured grids that are used in the atmosphere now, in the land model now. So there's still some work to be done with this, but we're headed in a good direction, which is pretty exciting. I want to talk a little bit about the 3 tags that we had last year for SysM main. The first one was 2201, and we added support for mountain glaciers. That was early last year. And then in May, we added updates for Calving and Calving MIP. So that you can see I'm not going to read all of this for you guys, but you can see that there's some really nice updates and included this one. And this, of course, is all Bill Lipscomb's work. I just made the text. And then most recently, we merged in November 25 a large refactor, including SMD and other SysM name lists. So the goal is to consolidate, increase the user friendliness of SysM through that. And the one that we're recently what we're working on right now is a PR to have exact restarts in SysM with changing processor counts. So this is a PR that's currently in review and will be the next SysM main tag. And we're not sure if it's going to be 2204 or if it's going to be 23 because it's a pretty big change. But it is backwards compatible. You can turn it off. So currently in SysM, if you change the processor layout of the model after a restart, you'll get a very similar result, but not exactly bit for bit the same. So because of some awesome work that Bill's done over the last few months, we now have an option available so that when you do that restart with any different PE layout, you still get the same bit for bit answer the next time through. And this is a standard for components in CESM, so it'll definitely be appreciated for across the modeling system that if you include an active ice sheet, you can depend on that capability at runtime. The algorithm is a little bit slower, so it's like a little bit more expensive. So if you want to run without it, that's still an option. And if you're running SysM standalone and you prefer to have a high performance run over, this particular feature, then that's absolutely still available. So it hasn't been tagged yet, and there's still a few things to work on, but it's the next one up. For SysM wrapper, so this is the part of CSM that interfaces between the SysM model and the coupling system for CSM. We had 8 new tags last year, and these are the ones that I wanted to sort of highlight. So there are updates to the SysM name list for all of the new SysM tags and software support. So if there is a new option in SysM, it should be available in CSM now as well. There might be a few that we didn't bring in, but if there's anything that anybody wants to use that you don't see in CSM currently, please let me know. I'm pretty sure that we definitely have that. We did update the default for the configurations within CSM. So the Greenland ice sheet and Antarctica had a previous set of default configurations, and we've updated those to take into account all the new changes within SysM. This isn't our final tuning set, Dave. But we're getting there. We have to do the spin up still. So yeah, we're definitely taking advantage of all the new features for the CSM3 and SysM3 releases. I wanted to point out that you can now run Data Glacier ComSet in SysM Wrapper. So SysM Wrapper is a nice sort of small checkout of CSM that only includes SysM and land model, which is mostly what you need to run most of the configurations that we use within CESM. So you don't need to have the entire model. But previously, you couldn't actually run the Data Glacier or Stump Glacier model in that configuration because of some missing steps. So that was one of the things that I've checked out this year. So now we can actually run that sort of replacement data glacier model from Scissor Mapper. So any changes that we make to Nameless, we can test to make sure that we're not messing things up for the other glacier model. One of the things that was required was a comp set to specify this. So there is a new sort of JK comp set is what I called it, because the J comp set was a one-off comp set previously, and I added my initial, so now it's just looking. And that is a CTSM data glacier comp set with all data models. So it's not exactly useful for much beyond testing, but it's kind of fun. And then Gunter has developed a lot of new grids for GRIS. Hopefully he'll talk a little bit more about, but those will be coming into CSM3 to support ISMIP and CMIP simulations. And we brought all those in through Scissor Mapper and CSM external already. So I wanted to put this up here as a code freeze. Here's Dave. And I missed the software engineering meeting yesterday, so I'm not entirely sure about how all of this is going to work, but I think we are deciding soon on the current configuration for CESM, which means that the atmosphere and the ocean model should be stabilizing the climate soon, and that will give us an option for spinning up the ice sheets with a stable climate in the future. Once we reach a full code freeze option, the tradition is to create release branches of exactly what we will have in SISM. So at that point, we can talk about exactly everything that is in SISM 3, and then test and document for the full release about 2 months later. One of the things I wanted to cover here is the GIA model that we started working with. So as a fun topic, and this is my husband in like snow that we used to have. You can't do that this year. So STICOM SVE3 is a glacial isostatic adjustment model. It is a fully three-dimensional mantle convection permitting model. It was written in C. It is very efficient on large parallel machines. And we've started working on bringing this in as a GIA component of CESM, which means that we can use the coupling system in CESM to send fields back and forth at runtime between the ice sheet and the GIA model to adjust for changes in sea level and topography that way. We've started building the framework for this, and then this fall we submitted a full proposal to NSF. So hopefully that will include resources for this work going forward. So this is just a slide from my previous presentation that I did about this. I think I talked about it more in depth last year. The work that we've done has been relatively minimal and mostly infrastructure. We haven't got to a point where we're fully coupled even close yet, but hopefully with this proposal comes in, then we'll have the ability to push this forward even further. And then, yeah, so this is the kind of thing CSM works around this hub and spoke coupler. If we have the solid earth model working through the coupler to update topography and sea level changes, we would need to add in the ability to do dynamic masking and surface elevation changes at runtime in the atmosphere, in the land, the river model, sea ice and ocean around the coast. It would be a huge change across CSM if we could get that far in the future. Zheng has started a project recently from a funded proposal called SciSwim, where we're including isotopes in all of CESM. And this is really exciting. So the Land Ice Group is working in this as well. So yeah, you can read this. And Zheng wanted us to, if anybody's interested in using water isotopes in your research, so actual water isotope tracers that include the phase transformations and paleo research or modern water tracer research. Here is a link to a user survey about how what scientific applications you'd be interested in and how you might foresee using that across the entire coupled earth system and CESM. It would be super useful. So I don't know how long I've been talking for. Hopefully it wasn't too long. That's all I've got for today. Yeah.
That's perfect. Questions for Kate?
All right. I know that went really fast.
Yeah. There's not a question, but an acknowledgement. Just that this isn't your only job. You're doing a bunch of other things too. So you've done an awful lot in support of land ice and
Oh, thank you.
in the past year. So we appreciate it.
I think Nicole had a question
Oh, yeah.
or not.
No, maybe it was just a thing. Oh, yes. All right. Oh, Tree, you can fill out that survey if you haven't done it yet. I'll put this back up just in case anybody needs to get that. There you go. Okay. Thank you.
Okay. Yeah, the last speaker is Gunther. And yeah, with news about what's to come.
All right. So hi again, everybody. I'm Gunther Legge. I'm a scientist here at NCAR. And so for this last talk, I just thought that I would just give a brief updates on what has been happening for CISM. And a lot of the slides that you're going to see are some that you have seen in previous talks today, but also the previous year. And so hopefully it is still informative. It's new for people who are not used to come here and talk a little bit more about what's to come in the next few months. So today we're going to make it somewhat official. We are officially releasing a soft release of CISM 3. Why soft? Because there's still a bunch of things to be done, and I'll get into this. But and part of the slide I'm going to show, it's about the journey that it took to get to where CISM is today, and the science that has been done with it. So when you do model development, whether it's like fully coupled model or just an ice sheet model, it takes a lot of effort, a lot of brain power, and a lot of consideration to make things work seamlessly. We have great minds to work that work on this here, and that helps to enable the science. So for the past year or two, I've been showing this plot like, okay, this is when we're going to release CISM, and sometimes I pushed the the deadline at the bottom. So, but we did say that in winter 2026 that we would release CISM 3, and so we have a soft release, and of course it's still going to be ongoing development, but we said that we would be done with some cleanup, documentation updates, testing, and so on. But I want to say at this point is that in terms of scientific capability, most of the science that we want to do with CISM 3 is already in CISM 3. There's going to be a few updates to come, but that are going to be minor compared to all of the work that's been into CISM 3. And those 4 arrows here, you can see that they change from orange to green. It's because they're underway, well underway. Still has started to do a bunch of code cleanup for a while. The documentation is still needs to be fully updated, but in terms of creating input files to be using CISM, there's some tools that are being prepared right now. It used to be a case where you had to put all of your information into one file, and then when you wanted to change one aspect of it, it could be cumbersome. And so we're creating those tools to make this process a bit more easier for the community and everybody. Kate has been working on the CISM test suite within the TSM framework, and more of it is going to be ready later. Of course, with the soft release, it doesn't mean that we stop everything that we're doing in terms of science. We're still, science never stops, and we're still working on new capability. As Kate mentioned earlier, over a year ago, Bill added some glacier capability in CISM, and of course, more development within this capability is ongoing. We're also working towards adding some more glacial isostatic adjustment physics. Right now, CISM has a very simple one-dimensional cell-only representation of GIA, but we are going to add some more capabilities that allow vertical variation, horizontal variation as well. And as Kate mentioned, we've started to add some SolidWorks capabilities into CSM, to which CSM will be coupled to. So for the start release, Kate said it already. So the main branch that has been tagged as 2.203 is considered, season 3-1 until the new PR, in which we had some, there was one bug fix that happened, and then so the producible sum capability is in. So, but pretty much this is season 3. So when you check out season, the main branch on the GitHub repository, you have the latest science capability for season. So in the next few slides, I'm going to give you a very wide overview highlights of the major updates that happened in seasons, like since season 2, which was 5-6 years ago. And I know when you come to these meetings, you see all these talks, and then you take it for granted, but there's a journey that it is there. And what's this journey from season 2 to season 3, what it really enhanced was capability of doing antarctic science. So in order to do antarctic science, you need to consider the ocean. Without the ocean, well, we don't have a good antarctic representation. And where it all started, it was with this MISMIP Plus, and MISMIP stands for the Marine Ice Sheet Model Intercomparison Project, in which, in an Adelaide setting, it was just a small channel, we were given a profile of melt rates that are extremely idealized to study the impact of this channelized ice stream. So this publication, there's a publication about it that was published in 2020, and this is how we started with setting some melt capabilities into CSM. It quickly evolved with some Antarctic-wide application on melt rates in different basins. Here you can see on this map, this uses not exactly the MB basin, but like very containerized some major basin in which we are trying to see the impact on melt rates, additional melt rates on the ice sheet. And these initiatives were led by with INIT-MIP, AWU-MIP, or LAR-MIP experiment. So here, there's a still basal melt rate that was given to the ice sheet model. We didn't do any parameterization or anything. It was given as a forcing. And it quickly evolved towards this MIP6 type simulation, in which now we were given ocean variables like temperature, salinity, or thermal forcing directly. And then we had to add some physically based parameterization within CSM to be able to convert these ocean fields into basal melt rates. And all of these capabilities are there. As you can see, we were provided with thermal forcings that cover the entire Antarctic ice sheet, even like at various depths, and also considering potentially that because the Grand Line could retreat. But very soon after that, we added capability to say that if you had an ocean model that ended at the Kelvin front and it couldn't circulate into ice shelf cavities, well, we could extrapolate the thermal forcing within the cavities and have them generate those melt rates for us. And finally, it's not necessarily in order, but we also ran a fully ocean ice sheet coupled simulation in the Adelaide setup with Gustavo Marquez, in which we had ocean circulation in the cavity. And in this configuration, the ocean delivers directly the melt rate to the ice sheet, and the ice sheet can respond and give some melt, freshwater melt to the ocean. You would wonder, why don't we do this? Is because, well, in global climate model, those cavities could be small, and the resolution of the ocean does not allow the circulation in such a small cavities. So the capability of this extrapolation of those ocean variables is still very valuable, but we're moving towards the capability of at least a new ocean model in CSM-6 to be at least circulating the biggest cavity like Ross and Ronnie ice shelves. Next, so there's a lot of MIPs involved in the previous slide. You can see NetMIP, AdWorld BASE MIP, MISO MIP, a lot of MIPs. And those MIPs, while they, it's a lot of work to submit to those, they also help guide the development of the capabilities in our models. So there's another MIP, Calving MIP, which helps us guide more the development on the Calving capabilities within CISM. And so this first MIP for Calving here, what it's trying to do is to assess and improve the approaches to Calving in iSheet models. So it's about the algorithm as opposed to the physics of the Calving. And we participated in it. The first phase was to test the algorithm in idealized domain. And you had, like, you can see here, 2 different domains. One that was just circular domain, fully symmetrical everywhere. And then you had at the bottom here, you can see a more complex domain. It's called the Tudor domain that is based on realistic geometry. And where the model participating to this initiative had to try to reproduce the retreat of the Calving front and then its readvance. You can see in the fully circular domain, CISM is doing a very good job of retreating for 500 years. And then when you stop the forcing that makes a Calving front retreat, it readvances to its original position. In the Tudor domain, a little bit more complicated domain, it retreated just fine, and then it's readvancing. There's just the relationship between the retreat and the readvance is not fully linear, so it might need more years to fully readvance to its original position. Next, we've been working on now the physical Calving law. So we have the algorithm, now we need to have the physics that allow the Calving processes to happen and compute the lateral Calving rates for the iSheet model. And for now, we are using a Calving law that's based on horizontal stresses at the Calving front that is similar to what Matthew Mollingham in his 2026 paper and what Bill in his 2019 paper are using. And what you can see, this was we had this attempt to add this physics-based Calving process into initialization for the entire iSheet. Here for the spin-up, you see CISM on the left-hand side. And you have some the difference plot versus compared to observation on the right-hand side. And of course, there's disagreement. But all in all, when you see that the Calving fronts are in pretty good agreement to where they're supposed to be overall. There's something to note here is that, at least as far as I know, and if you know otherwise, please correct me, there's no universal physics-based Calving law that exists to represent the Greenland ice sheet, the whole Greenland ice sheet, or the whole Antarctic ice sheet. It's still a very active area of study. As Tim mentioned, we also added a new initialization method capability into CISM. The traditional way that we've been doing initialization was to spin up CISM to a steady state, where there is no, when you started the model after the steady state, you wouldn't necessarily get the full ice thickness changes. You had to move the model forward a little bit, give it a little bit of a little push. But now we have this ice thickness change with time from the Smith et al. 2020, which gives us this those rates. And when you can add now this rate changes into the initialization procedure, so in such a way that when you start your iSheet model, you'll start with exactly those rate change that would be captured. So Tim did this in his paper, and he showed that if you apply these change rates over time, like you don't need much more. So for the Western Antarctic ice sheet to collapse, and it would take like over 1,000 years to add like more than a meter of sea level. Oh, sorry, like it'll be less than like after 500 years, you will get more of a meter of sea level. But if you wait long enough, just with what's happening right now, you would get a collapse rather quickly. Kate mentioned the glacier capabilities. So this is something that we added, and this is work that we did with Samer Minara, who's also here at NCAR now. And so CISM, being an ice sheet model, is now also an alpine glacier model. You can consider ice sheet as ice system now. And the novelty here is that most of the glacial modeling in the community were done with flowline models. And so CISM has been one of the first three-dimensional model to participate in this another MIP, glacial MIP. And here we participate in simulating the entire Alps domain and all of its glacier, over 3,500 of them. Here you can see on the left-hand side that the full alpine domain, and with those 4 squares representing those glacier systems. You have the Bernese Alps here that contains the Aletsch Glacier, which is the biggest glacier in the Alps. And if you run CISM forward with just the current climate conditions that we're in right now, within 200 years, you will lose more than 60% of the glaciers in the Alps. So we are going to move forward with additional capabilities for glaciers and modeling other regions such as Alaska or HMA, as I have on Asia. All right, other updates, of course, in terms of physics, I can go over everything, but we have new setting and sliding laws within CISM. We also have a steady state based hydrology scheme and so much more. There's also data about how to configure CISM when you are running with it. First of all, Kate mentioned the grid. So all of our simulation, whether it's the Greenland or Antarctic ice sheet, run on a 4-kilometer uniform grid by default. And those are the same grids that you would have in CSM when you run with an evolving ice sheet. We added capability for a hybrid restart. So when you're done with the spin up, typically you want to use that restart file to restart your model as an initial condition to do your science. Now you just need, before you needed to tweak this file a little bit, which was cumbersome, and now you just need to add a number in your configuration file, and it does it for you. We also added a block domain partitioning to speed up the model, which is very useful in particular for Antarctica, which has a lot of ocean sails. And so you don't waste processing power or computation time where there's nothing that's ever going to happen there. So you can partition the model to say, like, you don't need to do anything and concentrate the power you need over the evolution of the ice. There's then some improvement in the flexibility for reading input files, such that when in your configuration, you can just add several instances of CF input, and you can have several input files to start your model. And this comes in very handy because you need several fields such as ice thickness, bed topography, or geothermal heat fluxes, or SMB, etc. And sometimes you just want to change one of these fields. So instead of recreating a new file to add this one field, you can just add this one new field in this input file. And this duplication of input files is something similar is done for the output file. You can write as many output files as you want, and this comes in handy because you have scalar quantities that are very cheap that you might want to write at a higher frequencies than your 2D or 3D fields. So CISM3, we were pushing very hard to make sure that this CISM3 would come into CSM3, and it is there now. All of the physics that we did for Antarctica can be used within CSM. So all of those ice sheet grids I evolve are part of CSM3 now, including all the new physics. To produce some is in there, all the other software updates that Kate just mentioned. And even though, and right now we are working really hard to make the Greenland ice sheet a default evolution in CSM3. The capability to do the same for Antarctica is there, but we have not fully tested it yet. Just as a spoiler here, this is a short dummy run that we did with an evolving Greenland ice sheet over 70 years of the current configuration that we have in CSM3. And you can see that this was for the pre-industrial spin-up, and you can see how the ice sheet thickness is changing just over the 70 years with plus or minus 10 meters of thickness difference. So it's behaving well for now. So what's next? Hopefully by this summer we can give you a little bit more updates, like maybe less on the science, but more the technicalities about the streamlining for the input file creation, the documentation update, but also the land diagnostics that we've started within the QP initiative, which gather all the diagnostics from all the components within CSM. So more will be done until the summer. Future events, there's a CSM workshop in June, 15 to 17, 2026, here in Boulder. So we'd love to see you there again. And there's also the CSM summer tutorial, July 6 to 10. So if you'd like to know how to run CSM for your science, please register. The registration runs until February 17th, so closer soon. And if you have any question whatsoever at any time, if you want to learn more about how to run, configure CSM, or even within CSM, please contact us. I will answer all of your questions. So thank you very much.
Do you have questions for Gunter? From the remote? Well, if you have questions, maybe we put them together with the discussion.
Yes,
okay.
Let's do this. So for our last minute here, for the time that remains a little bit here, we wanted to have some discussion time. Everything is on the table, and anything that you'd like to comment on or talk about is welcome. And so that just 4 points, just to help things going, that we'd like to hear from you on how the research direction with CSM3 coming out and the new capabilities. What would you like to address as a community with CSM3, and what opportunities are there to research? What are the opportunities for model observation combination? We need to talk more with observationalists, and we're doing this more, but maybe there's even more that we can do. Are there barriers for the community in using the Landice resources and the model that we have currently? So we'd love to hear about all of this and how to make it better, but also talk about opportunities for collaboration with other working groups. So yes, if someone would like to say anything.
Or add a bullet point here, another topic of discussion.
So, can you expand at all on what your thoughts are on the glaciers?
Alpine glaciers?
Yeah.
Meaning for CSM?
CSM, yeah, or where that lands in a priority list and like that.
I'll go with that. The alpine glaciers are all terrestrial, and we want to expand the model to include marine terminating glaciers, in particular for Alaska, which is a region Summer's interested in, and ultimately the high Arctic glaciers as well. And so I'm going to work on adding that capability to the glacier model. And GlacierMap 4 is now finalizing their protocols, and they're asking a very quick turnaround. They want us to submit our regional simulations by around the end of this summer. And so we're going to generate as many regional grids as we have time to do, and then run the model in those regions. With the exception of the marine terminating glaciers, it's going to be pretty similar to what we did for the Alps. So we hope that once we have the regional grids, we'll have time to run the simulations and submit not all 20 regions, but at least, more than one region, maybe several regions to GlacierMap. And in terms of the coupling to CSM, I think we're not quite there yet, but Summer continues to work on adapting the hill slope scheme in CTSM to where you can simulate a more reasonable surface mass balance for glaciers at those smaller scales. And if we can do that, in a reasonable quantitative way, then we could start adding glacier regions to CSM as we currently add ice sheet regions.
Yep. If the hill slope becomes,
sorry,
if the hill slope model becomes the default configuration.
Yeah.
next generation CSM.
Yep.
Or not, maybe we need to talk about having regional hillslope specific terrain that.
Yeah.
Where it's needed, where those glaciers.
Yeah, that'd be good to follow up on.
Yeah. I think that we can do that. Yeah, I think shoot it. Yeah.
Do you envision a capability where CSM would run coupled for these glaciers for multiple locations simultaneously, or would they be done one at a time, or how would that?
There's no technical barrier to running multiple regions.
Okay.
So it's more a matter of whether the mass balance is good enough that it's scientifically interesting.
I would think that the other barrier would be whether you have bathymetric or surface topography underneath the ice sheet, underneath the glaciers.
All right. Glacier thicknesses historically the measurements have been very sparse.
Right.
But now through inversion methods and new satellite observations, they're gotten a lot better.
Okay.
Question in the chat. Way to set up System Antarctica to easily assimilate data from Antarctica in sync to transform the data that they will choose to collect.
Could Tree maybe describe Antarctica in sync?
Yeah, so in Antarctica in Sync is I'll say a measurement campaign. This is in Germany right now. And so they're taking community input about what data would need to be collected. So I'm just curious that from the perspective of modelers, I am not an ice sheet modeler. So is there data that would be of interest to, and especially in particular when they start collecting data, and it's only, for a several year period, but that might still be useful.
When you say assimilate data, do you mean like in a formal data assimilation way?
Yes.
We haven't developed SISM as a we haven't developed a data assimilation mode for SISM. So I mean, we have inversion where we can tune things in the course of a run to minimize the disagreement with some target. But does that qualify?
I'm not sure.
I mean,
I'm sort of stretching here. It's more of a like in a couple of days they're just taking community input now, and then if people here had something to say.
I mean, we're always looking for more accurate thickness targets and thickness targets that extend back a couple of decades instead of, and that's hard.
Yeah, the inversion would use the data to build a better model. It's just maybe not a full data assimilation.
Okay, thanks.
I feel like the term data assimilation gets more and more loosely defined through time.
That's true.
One of Gunter's questions was about barriers to participation. So is there anything, especially people online, anything on your wish list that would make your science easier? Make the tools easier to use? We know the documentation is way out of date, and that's on the list.
I am very happy to hear about the Docker.
Yeah.
Because I am working at the university, and having simplified versions of the real tools are really good for training people and bring them to the real tools later. So for me, this is a super plus that there is this Docker product together with CISM. Yeah, yeah. So documentation makes a difference for a lot of people. Things that these tools, the opportunity to run the model in a laptop opens, yeah, a lot of things. It looks like something really accessory, but
I agree. It doesn't seem like a big deal when you just toss it up there in a slide, but it actually the Docker environment really expands the ability for us to run on a lot of different places beyond just laptops as well. So there is a new cloud product that they're bringing in here at NCAR called Cirrus. And we can run some of these containers in the cloud, which means you wouldn't necessarily need the same supercomputing resources that we have currently. So if something were to happen and we lost access to some of the NCAR supercomputing, we might be able to use cloud computing resources to continue on. And having the Docker capabilities means that it's the same from the view of the user. And it's also nice for things like websites. I want to say like GHub. So we've worked with GHub a little bit in the past to host some data, and they have the ability to host tools or versions of software that run in containers from their backend, and in theory access their supercomputing resources, but it still looks like a Duratio environment from the container as far as it's concerned. So we're hoping to leverage the containers to be able to publish like online SISM simple tutorials as well in the future. That'd be pretty cool.
I'll just mention one other thing under discussion. As Summer has gone to meetings and presented the work using SISM for glaciers, there's been some confusion. Why are you using an ice sheet model for glaciers? Which she then has to explain. And so we've talked about within the Land Ice Working Group, doing after the CSM3, SISM3 release, a sort of rebrand of the model where a name that's been proposed as a community land ice model, which would be more reflective of what the model currently does and what we want to use it for in the future, and reflect that it now can simulate subkilometer scales. So that'll be something we'll be talking more about.
There's a competing also argument to keep SISM as a community ice system model as opposed to sheet model. So you wouldn't have to change the acronym.
Anyway, that's to be determined.
Yeah, go ahead, Betty.
So I'd like to hear a little bit more about the system diagnostics package and what its capabilities are. Will it be integrated into the running of CSM when you run with an active Greenland ice sheet, for example?
So yeah, thanks for this. There's two different diagnostics here. There's one that's within CSM, of course, that will be able to do just like what is done with all the other components. And right now we only have the key matrix in there as a template. And we've been gathering some input from the community to know more about what they would like to see in the diagnostics, because you can make it, you can plot as many things as you want, but this might not be desirable. And then there's the other part of the diagnostics for the community when they run SISM standalone, and whether we would want to use the same package for both cases. But it's in the work.
I can talk a little bit about Cupid, Betty.
Okay.
I mean, I don't know, maybe you could talk about it also. We were involved early on with Cupid, so I'm not sure where all of the stuff stands now. But so Cupid is set up to run automatically as CESM runs and produce diagnostics based on the configuration. You actually turn it on in the workflow in the case directory. So you don't have to do all of the complicated XML setup for each of the different components anymore. It just takes one XML file that is partially auto-populated by the case. And then creates the time series and the fields that are all populated as the model is running. So that's what they've been using. You've probably seen it at the project meeting for each of the cases that Cecile posted on the website. You can pull it up and look at the Cupid diagnostics on the GitHub page. Because none of the runs for none. Most of the runs so far for CSM3 haven't included active ice sheets. The ice sheet section of Cupid hasn't been populated. But once we start adding in active ice sheets, those will start popping up in there too.
So to that end, for everybody here, if there are any output that you'd like to see from the diagnostic point of view from standalone or fully coupled simulation, please let us know so that we could add it as we populate this. Any other comments or anything? Yeah, Jean?
The tools for creating input data set, is that available on GitHub now or still in development?
The GitHub page exists and I need to now push the changes.
Yes, you do.
Thanks.
So a lot of notebooks for the different input data sets exist. They're on Derecho. They're available for everybody who would like to use them. And now I just need to make them a little bit more comprehensive. But otherwise, yes, they're here.
I can help.
You will, don't worry. I might want to, I'm going to end on I don't know if it's a futuristic note, but it says that the current documentation, I would say, must have been very well done because we have someone who experienced to put the documentation into ChatGPT and have a simulation run, and he did. So
He just used the documentation to run via ChatGPT.
I don't know the area. So that was pretty good. I'm not going to put up that person on the spot, but I thought this was pretty cool.
So on the topic of AI, machine learning, besides what CG is doing, do you have any plans going forward with machine learning and the ice sheet model?
Yes. I'm not sure I'm allowed to say no to that. Right?
Absolutely, all AI.
All right.
One thing I'll say on that topic is, God, if I were younger, I'd love to learn all about AI.
Right.
But anyway, but even data is pretty sparse for most ice sheet things, and so in order to train AI on an ice sheet, you generally don't have the data. So a high resolution model is a really good way to train a tool. So I don't think we would, for that reason, I don't think we would be giving up our traditional model in favor of AI very soon.
But I would add to this that using AI in ice sheet modeling is very new. And there's going to be a first conference about it. Maybe not the first, but one of the first conferences just this summer. And we had someone from the LEAP project who started to do a little bit of AI using CISM. As it was a proof of concept as opposed to more like a scientifically directed study.
Yeah. I think we talked about, but haven't actually got into it yet, is ice sheet dynamical cores, velocity solvers, especially at high resolution, are very expensive. But chances are an AI could do almost as well, much faster.
The reason I asked is because that's sort of the approach we're taking in the sea ice model as well, is we're replacing parts of the physics. So our flow size distribution is one of the most expensive parts. And so we're developing a machine learning emulator for the flow size distribution. And so that will be in the CSM MLE version. So.
Yeah, for the GIA model proposal, we were very hopeful about the idea of having fast machine learning emulators for other more expensive parts of the climate system. So if you were running with the ice sheet coupled to GIA, you could use Camulator or Modulator for the ocean and atmosphere and do some very long-term millennial scale CSM simulations. That would be really, really cool.
Yeah, you had a question.
I was just wondering if that was going to be integrated into the model or if that would be separate.
That's too early to tell. It depends on what we can do with it and the benefits of it. One of the right now one of the benefits would be to use it for inversion. That's what comes first in my mind. And maybe the iSheet model is fast compared to all the other components of CSM. So in terms of getting 10,000 years, for us it takes a day. For CAM it takes
10,000 years.
Maybe less than that, but not too far.
That's an exaggeration.
So yes, this is a very good question. Okay, so well, if there is no other comments, question, or item of discussion at this point, if you think of anything, please contact us. But otherwise, let's close it. Thank you for all the speakers again. And we'll see you soon. And for whoever is here in person, please join us at the lunch cafeteria downstairs. Have a good day, everybody.
Thank you.
Thanks, everyone.